Sir, can you see the screen?
Yeah, I can see the screen. Um, your
Yes.
the recording is on, isn't it? Huh?
Yes. Yes.
It shows that the recording is on. Huh?
Yes.
Okay.
So we'll start.
Yeah, is everyone there?
It seems so, sir, 19 people. More will join, like, I think, when their turn comes.
Okay. Now, 1 second. How do I? Okay, so how do I? You have not put your video on yet, na? Group one?
No. Now we have put. Can you see?
Yeah. Now I can see you all. This is the best mode in which to see it. It's easier to see.
Yes.
And so I see two of you. Who's the third?
Naresh and Srinivas. So
Srinivas I can see. There's Naresh. Okay. All right. Why don't you start now? What we'll do is, because time is limited, I will not ask you any questions while you are presenting. Okay. So you make your presentation, and in case I have any specific questions, I will ask at the end of the presentation, unless there is something very pressing. Okay. On which I want to ask something. Okay.
Okay.
Just give me 1 second.
Yes.
Okay. So please go ahead. Now remember the time.
Yes, sir.
We have got
10 minutes total.
10 minutes in total for both presentations.
Yes. Yes. Yes, sir. We'll start. First, the idea is extracting core components from end-of-life products. We are focusing on two of the things, e-waste and polymers. So Srinivas will tell more about the first type.
Good morning, sir. So e-waste is an end-of-life product which comprises mainly of glass, ceramics, polymers, and many metals. So the metal constituents mainly consist of copper, which is 60%, and there are other metals like gold, silver, platinum, and dysprosium. So why is e-waste processing such a big concern? So there are 2 points to it. First, the treatment occurs in non-formal sector, which is 95% in India, which is unscientific and hazardous. So it leads to a release of large amount of poisonous gases into the atmosphere. And the second point is there is no focus on recovery of precious metals. Although some precious metals are in trace amounts, attention must be given to the recovery of these metals as it acts as a financial support to the recycling infrastructure. So this is a serious need for development in sustainable technologies to e-waste efficiently in India itself. So next slide, I'll tell about the extraction strategies. So first is the traditional method, which is the open air incineration and uncontrollable burning, which these are pyrometallurgical techniques like smelting, sintering, melting. So in these methods, fumes of heavy metals like mercury, cadmium, and lead are released, and the formation of halogenated dioxins occurs as well. This method is very expensive and energy intensive, and the selective recovery of metals is not possible using these methods. Hence, there are also another set of methods which are known as hydrometallurgical methods, in where series of acidic or caustic leaching are used to extract precious metals from solid materials using acids like cyanide, halide, thiourea. These are safer as well as more selective. So, because these are more selective, proper recovery of base metals from the solid material ensures enrichment of precious metals in the solid sludge left over, and thereby we can recover the precious metal recovery more easily. So the major disadvantage here is that it produces large amount of liquid sludge. Next.
Produces large amount of
liquid sludge due to the inorganic acids used in hydrometallurgical processes.
Yeah.
So the main idea here is to overcome both of these drawbacks. So both these drawbacks and the and hydrometallurgical processes are used. So in this process, various microorganisms are employed to generate organic acids, which are then used to extract metals from the solid sludge. So this is an established alternative route for extraction of copper and gold. On the right hand side, we can see that a study has been published wherein a researcher used different cryogenic bacterial strains to recover gold from waste PCBs and found a maximum of 14.9% dissolution of gold. So with recent advances in genetic engineering, I think it is possible to engineer bacterial strains which can selectively extract the precious metals from e-waste, thereby uh, moving forward in the e-waste processing technologies. Thank you, sir.
So the second part that we thought of was of polymers. So currently, these three things happen with polymers, which is reuse. That is the easiest way. You take plastic products, you clean them and use them again. Then there is repurposing. So you take those plastics and you make statues or other objects, or you use them in the road construction or etc. And the third part is recycling, where you collect, clean, and then reprocess them and then use them again as plastic. So in all three, that you can note that plastic still remains a plastic. So how do you convert polymers into something else? So there are techniques that use make fuels or lubricants from them, like polypropylene to lubricants or polyolefins to N-alkanes. So lubricants is obviously a petroleum replacement, and N-alkanes are have fuel value, and from N-alkanes you can also make other products. So you can see that in this you make a product which is of a lower molecular weight. So why do we need to extract these core constituents like we saw in e-waste? So suppose you have polyethylene terephthalate. So you use terephthalic acid and monoethylene glycol in this process, and of course you can recycle this. But why not try and recover this terephthalic acid and ethylene glycol? So it's obvious that the cost of PET is much higher than the raw materials. Otherwise, it's not beneficial to make this polymer. But what happens when the fossil fuels are depleted or very low and we have tons of polymers lying around? So at that point, this idea might become useful, like extracting those monomers. And so we know that polymerization reactions are highly exothermic, which is one of the most important reasons why this idea might be very difficult to implement. And there is a huge amount of heat that has to be supplied to break these bonds. However, some of these polymers actually depolymerize naturally. One of these ethoxyl ethyl cyanoacrylate is used in surgical sutures since the polymer bonds break after a certain time. So we have this dissolving type of stitches. So this polymer breaks down after stitching, which makes it uh, easier. So you don't need to remove the stitches after that. So we must use biodegradable alternatives or design polymers that can degrade when required. That is, they have sort of a timer in them. After a certain time, they will degrade. Thus, this idea of monomer recovery is not new. However, it's difficult to break these bonds, which is why it might face difficulties in implementation. So the equipment part of it is we focused on the Bosch process, Haber-Bosch process, and we will focus on the process development part of it. So,
Can I
Naresh.
just ask one question on
Yes, sir.
each of your presentations? I mean, at that point, okay?
Yes, sir.
Before you go to the next presentation. Right.
Yes.
Now, what I thought that in the biometallurgy area, although it looks like a very good idea, okay, and you are talking about having genetically engineered strains which are maybe more effective. But I think that one of the things that we'll need to look at is that an enzyme which is probably confined in the the active constituent is confined in the cell, and you've got a solid substance. How exactly does the reaction occur? I mean, how exactly do they see each other? What is the way in which these things penetrate into the core of the mask so that they can react? Have you found anything on that?
The bacteria actually when we put the solid sludge along with the cells actually release many organic acids into the mixture. So it is like the cells release proteins, and then we use those proteins to make antibodies. In a
Okay.
similar way,
So you're
these
saying that
bacteria,
it doesn't stay confined, it actually
no,
gets released into the culture.
yeah, it released into the mixture, and the metals
Okay.
actually
I've
gets
understood.
extracted
I've
from
understood.
those organic acids.
Okay.
Yes, sir.
Now, in terms of also the idea of using a biodegradable polymer, and you have given the analogy with the suture, but in those cases, I'm not really getting back the monomer. I don't know what
Yes, sir.
really happens.
Yes.
Do you get back the monomer?
No, sir. In that case, it is like it is essential that it is disposed of. But if we
Right.
design these materials with a say signal that if you reach that temperature, it might break down spontaneously, then the task of recycling becomes easier because then you just take them and once you apply those conditions, they automatically depolymerize. Like they have been
Yeah,
designed to
that's
depolymerize,
what you have to see whether they depolymerize or whether they
decompose.
go all the way decompose. You know,
Yes,
I
sir.
think
Like
that
that's the biggest problem.
you see, because if it is polymerization, then of course the energetics will again come into play. That these are very endothermic
Yes.
processes. Okay, but that's all right. There are so many things which are uphill reactions which are catalyzed by enzymes. That's fine, but you have to make sure that they are targeted for monomers.
Yes,
Rather
sir. Like
than just going into CO2.
yes, because that polymer bond will be one of the strongest in most cases. So
Yeah, I mean
to break
that
that,
that
others
part.
might
I
get
think the
broken.
analogy with the suture is good. I think the general idea of a suture is a very good thing, but just remember that there are basic differences between
Yes,
the two.
yes.
Hmm?
Like their recovery is not the priority, but
Yeah,
here that will be the
it's
problem.
just getting rid of it, which is the bigger issue, not
Yes,
recovery.
yes.
Okay. Okay.
So Naresh will do the Bosch process.
Yeah.
Uh, am I audible?
Yeah. Yeah.
So in the Bosch processor, we focused on the heat exchange and instrumentation part of it because you covered all the part of the material and lining design of jacket. So the first thing Bosch tried was heating the converter, the catalyst bed by externally using heating gases across the jacket. So the problems encountered were the temperature gradients were forming across the jacket, and at the high temperature, the low strength of steel was lower, and it caused the buckling and cracking of the tubes, and it also caused the explosion of tubes due to cracking, and the heat exchange was not sufficient, and hence Bosch had to use two another regenerators in front of the contact tube. So this was the configuration in the right side which was used, and further this spiral tube was also replaced by the vertical regenerator in order to avoid the pressure losses in spiral tube. So the next thing Bosch tried was to overcome the difficulties. Internal heating of converter was done by passing the syngas and air, and the heating was done by combustion of this mixture, syngas air. And for bigger production, then the Bosch found that the heat of reaction was enough for maintaining the temperature, and they just need to heat initially to reach the bed to the sufficient required temperature. And next slide. And after that, there were also some disadvantages associated with heating internally with syngas mixture. So gas heating was needed to be done in reverse mode with respect to normal operation, and this caused the cracks in the lining due to stoppages in the operation. And the heat supply at a single point, the heat supply was from the single point where here the air and syngas mixture is combusting, and this also led to temperature gradients, and gas heating was hence eventually replaced by electrical heating by using an electrical wire of 5-meter length, which was passing throughout the catalyst bed. So in this way, uniform heating was achieved. So the next part was the absorption of ammonia in water. So the strategies were followed by Bosch. First was co-current absorption in water. This was done because they wanted to avoid the water entailment back into the ammonia reactor. The second was then so this was the configuration of tubes in which water and ammonia were flowing in co-current direction. Because of the inefficiency of co-current operation mode, they tried to replace this co-current mode in terms of 3 counter-current stages. And after that, when the design of scrubber was achieved, they got the final counter-current absorption mode, which was the most efficient. Next slide. So the another thing was marvelous thing was that they built their own equipments, because today most of the instruments are available commercially, but at that time they built and tested their instrument in-house in the BASF itself. And some of the instruments were the pressure balance to measure the gas pressure. It was the previous version of manometer. Here U-tube and mercury was used. And the second was the density meter to record the densities of gas. So the next part of the instrumentation will be covered by Rajesh.
Not
I'll just
audible.
go. Yes, yes, yes. I'll go quickly because like we have only 1 minute left. So for oxygen detection in the nitrogen stream, what they did was like uh, they just introduced some hydrogen into a separate gas stream, and then they combusted it, and they could detect this water. So due to this reaction, they could record the thermocouple, the differential electric current, and due to that they could measure live the oxygen present in the system. And they use the similar system for carbon monoxide removal also. They use cuprous oxide, but that is for carbon monoxide removal. So that were our insights in addition to what you told us in the PPT.
Very good. Is it over?
Yes, sir.
Yes.
How did they, Nish, how did they purify the gas stream after the syngas combustion with oxygen? Because you'll have all these impurities which subsequently have to be got rid of. How did they do that?
So they heated the bed initially before the passing of mixture. So gases eventually drain out the combustion products, and then they pass the N2H2 mixture.
Yeah, so they basically did a purification in some separate vessel or something, and then regenerated the mixture and fed it to the converter. Is that what they did?
Yes, the from the N2H2 mixture, they did the CO removal and oxygen removal
Yeah,
before
that's what I'm
passing it
asking.
to.
Where did they do
Yes,
those?
yes. Sorry.
Where did they do those?
In the separate before
In a
passing
separate
the.
room. Okay.
Yes.
And you mentioned that the temperature went up when they did this reaction between syngas and oxygen, but there must have been a pressure build-up also, right?
Yes.
So, I mean, did they get both the required pressure and temperature with through this process, or they had to again repressurize it after that?
So the pressure thing was not mentioned, but the
Not mentioned.
temperature they reached by burning the syngas
Yeah.
to heat
Yeah.
the converter to required
Because
temperature.
it must have also increased the pressure. No.
Yes, it
Yes.
will increase the pressure.
Okay.
Because
Okay,
And
but I think it's a very nice. Both the presentations are very nice. What I will do is I will be giving your marks out of 10 for each presentation. Okay.
Okay.
All right. Is that all right?
Yes, sir.
Okay.
Okay, good. So the next person can begin, the next group.
Siddharth and Akanksha.
So the idea that we have chosen is artificial intelligence and chemical technology. Next slide. So this is a background of how AI has been the variation in artificial intelligence exhibited by computers, which is divided into 4 parts: machine learning, neural networks. Neural networks itself has 3 other categories, which is artificial neural networks, convolution neural networks, and recurrent neural networks, and then deep learning and reinforcement learning. Next slide. So why should we incorporate artificial intelligence in chemical technology is a question. And with some of the possible reasons are demand for automation. Today's processes are more continuous rather than batch. We are converting batch processes into continuous processes which require continuous monitoring. And that continuous monitoring would require automation, and artificial intelligence helps a lot in automation. The second reason is process modeling and optimization. We are striving to make chemical engineering a less dependent on empiricism, which requires process modeling and optimization. And there is an immediate need for immediate results because of due to the continuous monitoring that is required in today's industries. And also we are focusing on data driven models. Akanksha can continue from next slide.
Yeah, next time. So we will just look through one of the seminal artificial intelligence algorithms that were developed over time. So then the initial one that was implemented in chemical engineering was, if we have a certain raw material, and so what should be the intermediate reaction steps that need to be taken to get a product, and this has to be the most efficient way to reach to our product. So what they did was they assumed multiple reaction pathways. Each reaction was assumed to be elementary, or depending on like if it was hydrogenation, so what would be the typical kinetics of it. And they had thermodynamics data like heat of formation history, heat capacity, and they used these to model different reaction pathways and find out which process synthesis method was the most optimal. Next slide. So this is called an expert systems era, which lasted about a decade. So what happens in this process is this is dependent on knowledge. So this time what they did was they used to give certain governing equations. Like if you have a stirred tank reactor, what would be the temperature, residence time, dependence, and what is the thermophysical data of the entering reactants, and what should be the constraints, like the temperature should lie between so and so range and the pressure should lie within a certain range. So they had developed this as an if-else statement. So this is still a pretty rudimentary artificial intelligence algorithm. For example, if your process A was a stirred tank reactor, so if the conversion is not achieved in one reactor, so the if condition could be, should we add another reactor and proceed to the next step? Or if it is achieving, the conversion is being achieved, so we can directly move on to the next step. So this was the concept behind model LA, which was developed by Stephanopoulos in the 90s. Next slide. So this was known as the neural network era because previously neural networks were designed only for linear systems, because in image recognition, we don't need to know what is the mathematical model in between as long as it is predicting. But we cannot do that in chemical systems because we need to know the in-between steps should also follow the physical laws. So they had started with the bottom-up approach, where they felt that if you can easily model small units of a process, we can scale that up to a big unit instead of a typical top-down approach. And the reason this was implemented in chemical engineering was the mathematicians had developed non-linearity in the neural networks. This is one example where they had developed artificial intelligence software for developing a catalyst. So we had a catalyst library of different metals and surfaces with the typical turnover ratios, and we had certain chemistry rules like how is the adsorption occurring, or like what are the active sites. And we have HT kinetic data, which is high throughput experiments. So from experiments, we have certain kinetic data. So what they used to do was they used to develop different models, use a neural network to find the rate constant mechanism, And through this, they would find out which was the most efficient catalyst for a given reaction. This was how a catalyst design would be carried out using artificial intelligence. Next slide. So presently, there were three major tools that were developed. The first is an artificial neural network. So from a typical neural network, an artificial neural network is like it mimics how the neurons in the brain work. So it becomes a more complex structure. And then there is reinforcement learning, where we have our input and output data, and we are making the machine make decisions like if an X process is occurring, what should the machine decide that the next process should occur. So based on the previous data, it will decide what is the next data. So this is used in fault detection or in industries to find out if a certain error is happening, what should be the rectifying procedure. And the third is statistical machine learning. So typically in machine learning, everything is binary. It's either true or false. But in chemical engineering, for example, like the concentration at the outlet, it could be a range or a distribution. So people have started incorporating statistical methods to describe distribution of output. Next line. So these are two very recent examples that I found. The first one was they started incorporating the artificial neural.
Don't exceed your time. Huh?
Oh yes, sir. Yes, sir. So the first one is the oil production rate from a well, which they modeled using artificial neural networks. And the second one was operating a distillation column, where they used a first principles model where they developed the mathematics of the flow rate, and they incorporated a neural network to reduce the fluctuations in profit. Next slide.
So why is AI not more prevalent in chemical technology? Which is because chemical systems are very difficult to model even today. And there's a lack of interest in commercializing AI in industries because the conventional models are still functioning as effectively as AI today. And there was a lack of data and computational power back then in phase 1 and phase 2. And because of which there was no motivation or practicality at that point of time. And there were also intellectual challenges. People were not used to handling computational equipment as well as they are today. Next slide. But these problems are going away due to the following reasons. One is Moore's law, which has improved the computational power to a great extent, and data collection has become more prevalent. People are focusing more on collecting data and incorporating them in AI, and new programming languages like C, C++, Python have made coding more user friendly. Hence, more people are able to use AI and ML. And which was particularly the push for phase 3, which was to develop AI to outdo the existing technologies. Next slide. So based on what we have read and searched, these were our final opinions. Any model cannot be fully predictive, and any AI tool should be coupled with real-time data, which is hybrid models, data-driven plus first principles. We should focus on the basic scientific principles, but also rely on data to make our models, which is what is going to push AI in the future. But modeling systems with partial differential equations coupled with algebraic equations called as DAE is still a problem. Even though AI ML has improved over the last 40 years, we still do not have a concrete solution for the Navier-Stokes equation. Chemical engineering is highly empirical of all engineering branches, and that is a major stumbling block for the application of AI in chemical technology, because of which, due to its empiricism, AI is not seen as a very attractive method. But ML tools are widely accessible these days, so we can expect the applications of AI to expand in near future. Next slide.
As Santi mentioned, that AI machine learning tools have become very common, and this was one example that I encountered during my in-plant training. I wanted to describe that. So we have a highly non-ideal reactor, and we knew what was the flow rate and flow rate out data, but we had no idea what were the reactions occurring, what were the undesirable reactions, what were the desirable ones, and what was the reaction scheme. So I was guided to this process where we could describe a non-ideal reactor as consisting of a network of several small ideal reactors, each having its own temperature and residence time, because the non-ideal reactor had a lot of temperature variation. So if we had try to model this accurately with mathematics, there would be a lot of differential equations. It would be very complex. But by modeling it as a simple network of ideal reactors, the mathematical model was simplified, and we can use neural networks to find out what were the rate constants and how the reaction path, what the reaction pathway actually was. Next slide.
This was a second example of using ML tools which I encountered during my research project. So we were working on the extraction of acetic acid from water, which requires the estimation of partition coefficient using thermodynamic models. And the one that we chose was unified. And its activity coefficient calculation includes combinatorial and residual activity coefficient, which is called as gamma. So combinatorial is very straightforward. It is fully predictive. Meanwhile, residual is semi-predictive, which has a parameter called AMN, which is the interaction between groups M and N. And next slide. So to we had to train the machine to correlate to calculate unifact data according to a given experimental set of data, which was done by modifying the A parameter using the original parameter calculated from unifact into the weight function. And then we split the data into 20% testing and 80% training data sets. And it was finding a good fit at lower values of partition coefficients. Next slide.
Yes, okay.
So the first part is over.
Yeah, one of the things which you mentioned, which I thought that can open up.
राजेश ने शेयर
is-
करिए. अरे
Can you hear me?
Yes, sir.
Okay. No, what you said is that one of the difficulties in
राजेश ने शेयर
applying
करिए.
these techniques is that chemical engineering has a lot
I
of
changes the
restrictions.
trainer.
Now, what is required to reduce the degree of empiricism? You remember that when we were looking at Pascal's constraints, and we said a lot of things about how do you reduce the degree of empiricism.
Part 1 to
That's what applied research is all about. So, what is it? Can the degree of empiricism be reduced?
Yes, we can create approximations of our model. Like I described, if we have a highly non-ideal reactor, instead of going into the accurate mathematical model, we can create a simplified model which is very close to what we have. So that's kind of a stopgap measure that we can take. Like
What
we
I
can
would love
approximate.
to see is, because this is a very important area, and what I would love to see is that if you can take it forward, and identify specific, cases where you can attempt to reduce the degree of empiricism, okay, in particular facets of chemical engineering, okay.
Okay.
It really opens up a lot. A lot of people can then work on those aspects. All right, thank you. Next one, and you have to go a bit faster because
Yes,
we've really exceeded time.
Yes, sir. So next slide. Yeah, so we'll skip this part. Next slide. So Vladimir Hensel's research mostly focused on catalysis, and he was responsible for the commercialization of platinum as a catalyst in the platforming process, which will be discussed later. And the platforming process was very pivotal because it was producing a lot of hydrogen from the dehydrogenation reaction, and also a lot of aromatic carbons, which were later incorporated in the plastic industry. And his platforming process was also pivotal in developing catalytic converters. Next slide. So before platforming process, the industry used to use thermal reforming, where we used to have crude gasoline going into a cracking reactor, and at around 800 Kelvin and pressure between 30 to 70 bar, the dehydrogenation reaction used to take place. And they used to feed it to a fractionator, where we used to get the upgraded gasoline with aromatics with a higher octane number, and the light hydrocarbons were again sent, which were mostly methane, ethane, butane. It was sent to a mild reformer to create more aromatic compounds, and then we had certain residue. but the octane number was still not high enough. It used to, like, even after this process, it would go up to like 65 or 70. So people used to add anti-knocking agents like tetraethyl lead to increase the octane number. Next slide.
So platforming process was the major accomplishment of Vladimir Hansel, where he recognized that only the surface atoms of a platinum catalyst actually assist in the catalysis of the reaction, and he made out that only 0.01% of the total surface, if embedded with platinum, is actually able to give the desired conversion. So what he did was he used alumina as a support, and alumina with silica as a support, and he embedded platinum catalyst particles, which people now today focus as the nanoparticle technology. And he also found a way of degenerating the spent catalyst by using sulfuric acid, because there was formation of platinum alumina silicates, and treating it with sulfuric acid would regenerate the pure platinum. So the use of alumina as a support was another important aspect, because alumina is a Lewis acid, and due to which the paraffins in the feed would actually dehydrocyclize to form aromatic compounds. And this was another pioneering invention, because aromatic compounds actually opened or bridged the petroleum industry with the plastics industry. And due to this hydrocyclization, there was also presence of a hydrogen-rich gas which was being formed. And this hydrogen-rich gas was used in hydrotreating sulfur and nitrogen compounds so as to reduce pollution. So Vladimir Hansel's one stroke of using platinum was a master stroke in 3 different industries. Next slide, please.
So this was the graph I got from Hensel's original paper, where he was comparing the thermal reforming versus the platforming process. So the bottom graph, which I had circled, was without any anti-knocking agent. So at about 80% yield, we can see that the octane number with the platforming process is about 90, while for the same thermal reforming process, it comes to be about 70. Because the octane number was so low, so in the upper part of the graph, they used to add tetraethyl lead 3 ml per gallon of gasoline to bring it to the level that platforming process was giving without any anti-knocking agent.
What are the two axes?
The y-axis is octane number. It is split into 2 parts. So the bottom part is without anti-knocking agent, and the above part is with tetraethyl lead. And
okay, so the y-axis is the octane number. Huh?
Yes.
And what is the x-axis?
That's the gasoline yield.
Oh, the gasoline yield. Okay.
Yeah, they've done it 100. They've written it in descending order.
Okay, so what happens to the rest of the gasoline?
The rest of the gasoline mostly contains residues or light hydrocarbons, which could not be converted to aromatics like methane, ethane, propane.
Yeah, so it seems to me that one of the big advantages is not just reaching the high octane number, but if you look at the gasoline yield, that was much higher. You know, it's nearer to 90%. You know? So it's really, I think, the yield which actually drove as much as the absolute magnitude of the cracking, you know, and the octane number.
Yes. So people, with adding an anti-knocking agent like tetraethyl lead, it went even higher, like for the same 90% yield.
Right.
But its lead is toxic, so people are shifted to ethanol instead of lead.
Okay.
Next slide. So this is just a summary where previously with the thermal cracking process, you used to get 65 octane number fuel. And there was an introduction of tetraethyl lead, but there were a lot of environmental concerns. So this was where Hansel at UOP pioneered the platforming process. Previously, platinum was considered to be very expensive, but platinum and alumina support. Hansel argued that in the long time, the costs will the cost won't be much because of the high value addition that we get from generating hydrogen from the dehydrogenation reaction, and also the aromatics like benzene, toluene, xylene, which were later used by the plastic industry. And this hydrogen is used for treating the crude gasoline which enters the reformer, because if the crude gasoline that contains sulfur and nitrogenous compounds, it can deactivate the catalyst. So by hydrotreating it, we can convert sulfur to hydrogen sulfide and nitrogen to ammonia. So we can prevent the deactivating of the catalyst by the hydrogen that we get from the platforming process. Next one.
You have to wind up now.
Yes, sir. The last slide, sir.
Actually, you have taken much
yes, sir.
longer, no, almost 20 minutes.
Yes. Yes, sir. So Hansel initiated the process of making catalytic converters, though it was pioneered by French scientists Eugene Houdry and Americans John Mooney and Carl Keith. Hansel directed it in the early 1960s at UOP, and the foundation was platform catalysis, as we can see in the figure. The catalyst active material here is also platinum, which is embedded on an alumina support, and this catalytic converters is nowadays used in vehicles and vehicles for conversion of NOx into reduction of NOx and other poisonous constituents into lesser into innocuous compounds. Thank you, sir.
Okay, thank you. So now what will be very interesting is, when you go to biofuels now, because if you have to really, the fossil fuel days are numbered. What you'll have to see is that in the case of biofuels, and maybe through Fischer-Tropsch synthesis, when you get such biofuels, how exactly these processes will continue their relevance. So I think that because you'll be coming at it from the other side, from a small molecule, you'll be making big molecules, rather than from a big molecule breaking up and making smaller molecules and reforming. So have a look at the future relevance of these technologies. Okay. Okay. Thank you. Next group. But time, you have exceeded your time, so please try to stick to your time. Otherwise, we'll require another hour later on.
Okay. So good morning, everyone. We are going to present some alternative forms of energy that are available as of today. Next slide. Solar energy is an essential source of renewable energy, and the photovoltaic
Prakriti, who is there with you? Is it Harsh?
Harsh and Devarsh.
Yes, sir. All three of them are there?
Yes, sir.
Okay, okay. Just keep your one of you is I'm not seeing you, So just okay, that's all right. If you're there.
And its most adopted form is the photovoltaic cell. The large magnitude of solar energy makes it highly appealing. The first solar cell was constructed back in the 1880s by Charles Fritt, and since then, silicon-based surface activation technologies have been incorporated into these cells, upping their efficiency to almost 47%. And as of 2021, solar energy is cheaper than fossil fuels. Hydel energy is another major renewable source of power. The first Hydel scheme was developed back in the 1880s again by William Armstrong to power a single arc lamp in his gallery. Since then, hydel energy has grown to the extent that today the US has more than 2,000 hydroelectric power stations, accounting for 6.4% of the country's total electricity production. Next slide. The concept of using falling water to generate electricity was first introduced in the US and in Europe in the 19th century. The first tidal power plant was set up in France in the 1960s. And in 2011, the Shiva Lake tidal plant was set up, and it has a total power output of 254 megawatts. Geothermal power has been identified as a source back in 1400s, but it was only in 1911 that the first geothermal plant was set up in Italy. In 2006, a binary cycle plant was set up in Alaska that has the capacity of generating power even at 57 degrees Celsius. Next. Wind power today is a sustainable and popular source of renewable energy. It has come a long way from the 9th century, when windmills were set up in Iran to pump water and grind grains, to the 1990s, when the first offshore wind farm was erected. Today, the US has reached a capacity of 60 gigawatts. Next. Back in 1853, Patrick Duffy conducted the transesterification of vegetable oils. This was 4 decades before the first diesel engine was even functional. And today, the biorefinery concept has taken over. Biorefineries, analogous to petroleum counterparts, are being set up to better incorporate a circular economy. Next. Nuclear fission was first discovered in 1928, and the first nuclear reactor was made in the US in 1942. This grew pretty quickly, and in 1956, the first commercial nuclear power station was set up in England and connected to the national power grid. Next. Hydrogen fuel is quickly gaining commercial relevance as a zero carbon fuel that has applications in fuel cells as well as internal combustion systems. In 2011, UTC Power was the first to commercialize a large fuel cell for use in universities and hospitals. Next.
Okay, so let's talk about the present scenario. As you can see,
Just speak a bit louder. It cannot be heard properly.
yes, sir. So as we can see on the slides, while hydel and tidal energy have very high energy efficiencies, the rest of all the other energy sources have pretty much the similar efficiency, with the exception of geothermal, which is very low. Also, renewable energy sources make up a very small proportion of the total electricity production, and hence, as we can see, we are extremely reliant on fossil fuels, where their contribution is almost 85%. Next slide. So here we take a look at the limitations and drawbacks of all the energy sources that we have discussed. While for most of the renewable energy sources, a common trend that is seen is that they cannot be applied everywhere. Like energy and electricity production cannot be used everywhere. Also, another common limitation is the high initial capital cost or the high maintenance charges. While hydel and tidal power may pose a threat to aquatic life, nuclear fission has other problems of waste disposal. While solar PV do not have such problems, but the energy storage itself is a huge hurdle. Therefore, a substantial research and development is required to make these sources more practicable. Next slide.
So let's talk about the future. The solar energy is on the verge of a major change, with perovskite and multi-junction PV to be the solar cells of the future. The work is also being done on developing photovoltaics. Nuclear energy can be sourced from an entirely different process of nuclear fusion, while also making the process inherently safer with generation 4 reactors. The wind energy can be obtained in the future from artificial trees and other vertical designs, harnessing the wind power and also exploring offshore wind farms. Biofuels as drop-in fuels can be a reality in the coming years. Increased yields using the new catalysts will make the biofuels cheaper than fossil fuels. Hydrogen fuel cell technology is set to become cheaper with the expected decrease in the energy costs, and also storage and transport of hydrogen will become easier and affordable than it is today. The fossil fuels will be used to a lesser extent, and carbon capture will be opted for on a large scale. And we here pose a question that whether replenishment of the fossil fuels can also be an idea. Next. So alternative energy sources have the potential to replace the previous slide, I guess.
Yeah. It's a good overview, but it's always good, in these kinds of presentations to focus on something a little more narrow, because otherwise, it could be more like an overview, which is fine. I mean, I think you've made the case very importantly. And as you've said, that 85% is still fossil fuel. So I think that, a little more on how exactly this trend will shift, that could have been perhaps, a little more emphasis, and perhaps even in the Indian context, that which are the ones where we should focus, would have been useful. Okay. But otherwise, it's a very good overview. Please carry on.
Yes. So now let us move to the next presentation. Awesome. The chemical engineer who changed the world, according to us, was undoubtedly Carl von Linde, who was the co-inventor of the air liquefaction and separation processes. Next. Carl Paul Gottfried Linde, honorably known as Carl von Linde, was a mechanical engineer by profession, and his work was focused on cryogenics, physics, chemistry, and engineering. William Hampson was a barrister by profession and taught science and engineering to himself. He independently filed process patents only 14 days prior to Linde, with both of them claiming for the same process. Next. So in 1873, Linde made the first refrigeration system for the Spartan brewery using dimethyl ether as a coolant. And after that, he moved on to ammonia due to its favorable thermodynamic properties to be used as a coolant, which is still in practice today. And in 1879, he started the Linde Ice Making Company and sold refrigeration units to breweries, and also had sold 747 of such units by 1890. And in 1892, he received a request for carbon dioxide liquefaction system from a brewery in Dublin. And this triggered his work on air liquefaction, which commenced in 1894. And just after about an year, he filed the process patent for the same on 5th June 1895. In 1901, he started his work on air separation and it was successfully completed by 1910, along with his son Friedrich and co-workers. Next slide. The Hampson-Linde cycle is a positive feedback cooling system, which is completely based on the Joule-Thomson effect, which states that the real gas below its inversion temperature cools on expansion. So the process was similar to the Siemens cycle, except for the moving piston, which made the gas to do work. The Siemens process was mainly developed for refrigeration and not for air liquefaction, which may have been the inspiration for Linde to work in this area. Next.
The main elements of a simple Linde-Hampson cycle are listed here. The system consists of a heat exchanger and a Joule-Thomson expansion valve. The fluid is isothermally compressed and then passed through a heat exchanger for cooling below the critical temperature. This cooled gas is then expanded through a JT valve to produce a two-phase mixture. The liquid is then evaporated by absorbing heat from the refrigerated space, which acts like an isothermal source of heat. Next. This process can be represented on this thermodynamic diagram. Rajesh, could you just move your cursor over the points as I talk about them? Okay, so from point 1 to 2 at a constant temperature, the pressure is increased. Now the fluid enters the heat exchanger and gets cooled at constant pressure. That's from point 2 to 3. From point 3 onwards, the gas expands isenthalpically up to point 4, where the pressure is the same as our initial pressure. This is why we had initially pressurized the gas. The dome now shows the two-phase region. We assume that the gas and liquid are at their saturation points. Now this gas undergoes a phase change, and the saturated vapor is taken back to the compressor inlet with no overall pressure drop. Next slide. The Siemens process can be considered a precursor to the Linde-Hampson cycle. However, it failed to achieve 100% liquefaction. Its objective was to obtain work from the gas expanded. The Joule-Thomson effect, along with the Siemens process, led to the innovation that is the Linde-Hampson system. Linde's genius was that he developed the first commercial refrigeration system that helped in the complete elimination of ice boxes in the food industry. He saw the potential in the refrigeration system and expanded it to other industries. Later on, while working on cooling using carbon dioxide, he discovered that the Joule-Thomson effect can be used to liquefy gases, and subsequently he expanded this idea to air separation. Next.
Okay, so as we can, we'll discuss about the thought.
Speak a bit louder.
Sorry, sir. So we can look at the thought behind it and also the significance and the current implications of the process. So Linde drew inspiration clearly from the Joule-Thomson effect and possibly the Siemens cycle. His interest in refrigeration and cooling was driven by finding alternatives to ice cooling, which was prevalent at that time, and also by developing a method for continuous air liquefaction that was the first at that time. It was instigated by the request for liquid CO2 by the Guinness Brewery, and he also disproved the Boyle's law, which was thought of to be correct at those times. Next slide. The importance of liquefaction of air is indirectly portrayed by the industrial and the huge demand for the liquid oxygen, nitrogen, and argon. While liquid oxygen is used for metal cutting torches and as an oxidant for rocket fuel, it is also currently used to provide oxygen to patients who have breathing problems. Liquid nitrogen is used in cryogenics and for refrigeration and cooling. And also liquid argon is used for many applications as it provides an inert environment, so it is used in argon gas discharge lamp, and it is also used in to provide an inert atmosphere for growing silicon and germanium crystals. Next. So thus we conclude our presentation with these two significant figures in the history of science, and would like to thank you for listening to us.
Well, yeah, thank you. I mean, I think it's a very comprehensive presentation. I don't know, would you like to give credit to them for disproving Boyle's law, or somebody else, the people on whose work all of this is based?
Yes, sir, but as we discussed, the Siemens cycle was that was the precursor that we considered. It was mainly done for cooling and to perform work using a gas. But here they showed that we can cool it and then we can liquefy the gas as
So
well.
what would be the future advances which one might be able to think of in this area? Do you see any possibility of in fact, it's not very clear that what happened with the liquid carbon dioxide. What happened there? Did they achieve that? Or they just kind of switched over to liquid air?
So that liquid carbon dioxide was it was requested to Linde. So I think
know, but did he accomplish the task?
Yes, sir, he
Why
did
not?
accomplish the task, and then he extended this idea to air separation.
Yeah, no, I'm just saying that, of course, today you get dry ice. That's, of course, quite common. But in the area of carbon dioxide, this is going to be of very critical importance, especially with all these greenhouse gases and all. I don't know whether there is an opportunity to look at these technologies for CO2 removal. So maybe there's an opportunity to look into that area. Okay. Thank you.
Thank you, sir.
Yeah, so our group today will be presenting about carbon capturing and utilization technology. Next slide. I have targeted a very specific problem statement about this, and which is that a lot of methane gas or natural gas is flared in the oil rigs, which is a polluting gas, and it right now it cannot be stored, or because of safety issues, and also that these companies aren't ready to put money into this technology yet. So basically around 70 billion metric tons of natural gas is just flared into the environment or after processing it safely. But the thing is, we can use this natural gas. Methane is actually 80 times more dangerous of a greenhouse gas than CO2. That is why methane is burned into CO2 and then it is released into the environment. So
70 metric ton or million metric ton?
It's a billion metric ton. I've missed the billion in my presentation.
Okay. Just correct it later on. Huh?
Yeah. And so basically, our goal is to either use the natural gas in a efficient way, or even if it is burned away, to capture that carbon dioxide and make it use it in a more economical way. And the ultimate goal is to form an anthropological carbon cycle, so that this carbon stays in the environment, and we don't require more of this petrochemicals to be at least reduce the dependency on the petrochemicals. Yeah, next slide. So this is the current technology that is being used. Basically, methane is steam reformed to syngas. And the drawbacks of this is basically this reaction is very energy intensive. It requires more than 700 degrees Celsius, and it is also a sort of an obsolete technology because it was developed in the mid 90s, basically from 1930s to 1960s. So this is actually a very important reaction. I'm not asking more natural gas to be diverted. I'm just saying that the natural gas that is being flared, that can be used some other than from this process. So right now, as it's seen that methane is converted to syngas, and that syngas, what the idea is, either can be converted to methanol, or it can also be oxidized further to carbon dioxide, and then also it can be converted into methanol. Next slide. Okay, so these are the potential novel technologies that are being looked at. So right now, if methane has to be oxidized, all of it oxidizes to carbon dioxide, and then that carbon dioxide is or carbon monoxide, and then it is converted into methanol, which is a good biodiesel, a biofuel. So what the idea is that we can selectively functionalize the methane. So one of the hydrogens from the four hydrogens can be functionalized with the hydroxyl group, so that a long process such as that of steam reforming is not required. So this technology is being worked on. Either we can use these zeolites, which can be used as a catalyst, and the temperature conditions are quite more less intensive. So that the solution is to actually when the methane can be collected, and even while transporting or nearby, it doesn't need a very big plant, so it can be converted into methanol with less capital. And another reaction that we were looking at is we can use photocatalyst, very specific photocatalyst, that is cerium catalyst. And with coupling agent, we can LMCT is basically ligand to metal charge transfer, and HAT is the hydrogen shifting, like hydrogen is basically being shifted and a functional group is being added. So these are the two ways which I found out where methane with a less energy intensive way can be converted into methanol without all the intermediate steps. Yeah, next slide. So now coming, as I said, we'll be looking at two ways. So that was the methane way, and now we'll be looking at how to convert carbon dioxide directly to methanol, which I think was a groundbreaking thing. And there's only one. The very fascinating thing is there's only one commercial planet in the whole world that is converting carbon dioxide to methanol, and that is in Iceland. And this is because methanol is almost produced in half the money that half the capital which is being spent to convert it directly from carbon dioxide. That is why this has not been commercialized in a more larger scale. But in Iceland, they're doing it because there's a abundant of geothermal energy in that area. So this is the direct hydrogenation. So they follow the direct hydrogenation of carbon dioxide to methanol, which occurs at just above 200 degrees Celsius, but it costs twice as much than producing methanol from natural gas. I would like to point this out that in 2019, I came across a wave in which Indian Oil also developed a strain of algae that produces lipids from omega-3 fatty acids, and they convert CO2 to methanol. But there's only one 1 kg pilot plant that is available in their disposal. So the difficulties, since I said that it can't be scaled up, the main difficulties is that CO2 to methanol conversion has a very low rate constant. It is close to 10 raised to -7. That is at 200 degrees Celsius, because suitable catalysts haven't been found out to lower the temperature. So our aim is to find suitable catalysts so that the temperature can be lowered. And at 160 degrees Celsius, the rate constant becomes 10 raised to -5, and it further reduces when the reaction reduces, so that the reaction is pushed towards the right, and methanol can actually be produced in a more scalable way. Yeah, next slide. So as I said, this was the ultimate goal. Right now, we are pretty good at burning the biofuels and releasing the carbon dioxide in the air. So what we have to do is capture the carbon dioxide, convert it into fuels again, which I said can be done either by methanol or ethanol or any kind of other fuels that can be generated from carbon dioxide directly. So in this way, we can conserve the amount of CO2 in our environment in a constant way, and we don't need to dig out more petrochemicals or more fuel providing, energy providing materials in the future. So this is the way we can ensure a sustainable future. Next slide. Yeah,
No,
so that'll be our presentation.
why in the first place do they flare this natural gas? What is the reason?
Sorry,
Why do they flare the natural gas in the first place?
a blame.
No, why do they burn it?
They burn it because methane is 80. It captures more heat. It has more heat capacity, and it's more dangerous of a greenhouse gas in the oil rig. And CO2 is 80 times lesser of a greenhouse gas than methane. So they would rather have CO2 in the air than methane in the air.
No, is because they are recovering natural gas in any case. Is it that there is a surplus of natural gas?
No, so basically, when oil rigs are digged up, there is natural gas that comes out from the ground and which cannot be captured economically. So they just vent it out in a certain way and they burn it away into the environment.
Right. But what I'm saying is that's the point, that if that is the issue, then converting it into methanol, right, would still that problem would still remain, right? How I will take it out in the first place, in the
Right.
vegetable form. So I think a little more deeper understanding of why the methane is vented out, I think would be helpful. Okay. Just so that otherwise you can do all of this and people will say, but this is the problem.
Okay.
So I think just try to go back and try to figure out why that is the case.
Okay.
All right. Okay. Go on to the next one.
Good morning, sir. The chemical engineer who changed the world with his steelmaking process, Henry Bessemer. Henry Bessemer was an English inventor from 1856 until 1950, whose steelmaking process became the most important technique for producing steel in the 19th century. He played a significant role in the development of Sheffield as a major industrial center. Bessemer had been trying to reduce the cost of steelmaking for military ordnance, so he devised his technology of blowing air through molten pig iron to eliminate impurities to minimize the cost of steel production for military weapons. Steel manufacturing became more accessible, faster, and less expensive, which revolutionized the structural engineering. He is one of the most important second industrial revolution inventors. The invention from which Bessemer made his first fortune was a series of 6 steam-powered machines for making bronze powder used in the manufacture of gold paint. Next slide. How was he introduced to steel? During the Crimean War, Bessemer invented an elongated artery shell rotated by the powder gases. However, the French authorities with whom he was negotiating pointed out that their cast iron cannon would be ineffective against this type of shell. So he then set out to create a more durable cast iron. Bessemer discovered that blowing air through melted cast iron not only cleaned it but also heated it, allowing the refined iron to be poured more easily. The reaction of oxygen with carbon and silicon in the iron causes this heating effect. He used these new techniques, which later became known as the Bessemer process. He soon produced large slag-free ingots as workable as any wrought iron bloom, and far larger. He invented the tilting converter that you can see on the right, into which the pig iron could be poured before the air was blown in from below. Next slide. Steel manufacturing process, the Bessemer process. The best feature of the Bessemer operation, which strikes us most wonderfully, is that cold air is blown in great quantity through melted pig iron, and yet the iron is hotter at the end than at the beginning. For example, if a fuel were on fire in the converter, it would certainly be made much hotter by the air blast. Similarly, the oxidation or combustion of part of the ingredients of pig iron furnishes all the heat required for the process. For example, 10 tons of pig iron contains some 350 kilograms of carbon, which all burnt out in the mesmerization, furnishing heat equal to the combustion of some 400 kilograms of coke. Since it is burned and its heating power is utilized in a very few minutes, hence, even though cold air passes through the iron, it becomes even hotter, which removes all impurities and pure iron remains, making it even more vital. Next slide. His other inventions. He has over 100 inventions in iron, steel, and glass. From 1838 through 1883, Bessemer was his prolific inventor, holding at least 129 patents, military weaponry, movable dies for embossed postal stamps, a screw extruder for extracting sugar from sugarcane, and others in the iron, steel, and glass industries. In 1857, Bessemer was granted a patent for casting metal between counter-rotating rollers, which was a predecessor of today's continuous casting techniques. Interestingly, Bessemer's original idea has been realized in the continuous direct casting of steel strips. Next slide. Honors and legacy. The pioneering innovator Bessemer was awarded many honors for his contribution to science. In 1879, he was conferred upon the title of knighthood and was even inducted into the Royal Society of London. The American Academy of Arts and Sciences honored him by nominating him as their foreign honorary member in 1895. In 2003, Bessemer was named among the top 10 technological innovators in human accomplishment. So to conclude, Bessemer was an important part of the Industrial Revolution. His innovations changed the steelmaking process, and he is an important figure in history. Next. Thank you.
Where is Mohammed Pasha? I thought you had 3 people, no?
Yes, sir.
Where is he?
Sir, I'm here, but I helped. I made the PPT and I collected the information.
Huh?
So, can you hear me?
Yeah, I can hear you.
So, sir, I made the PPT and collected the information, and so I contributed
You
there.
allowed
and
them to present, and
yeah, because of the
but you were
time.
involved in the
Yes, sir.
work. Huh?
Yes,
Yes,
sir.
Part of the work, both
Yes, sir.
both
Yes.
presentations or one?
So some more of this of the scientist Besma one. I made the whole PPT and
The Bessemer.
yeah, yes, sir.
Okay. All right.
So, can I answer your question, like partially answer your question? The one.
Yeah.
So basically, methane, where the petroleum is extracted, the methane plants can't be set up. Basically, it's more of a petroleum extracting location. So it's more of a economic thing. But with this technology, which I was talking about, how it can be converted to methanol, there can be remote plants can be set up in a smaller scale, so that whichever oil rig is producing the methane, since not all of them, like if it's offshore or onshore, then it can be stored in a more smaller way and it can be converted into methanol.
Absolutely. In fact, what I was thinking is, you see, those technologies are quite well known. Like methane going to methanol. Okay. In fact, I'll send you another very promising technology which has been worked out by Sunny Chan in Caltech. Which is a copper primer. Which does the job. But I think the bigger problem is really the logistics of taking the methane out, and
Right.
maybe, as you said, putting it into a remote location or whatever. I would say, just try to focus a bit more on that part.
Okay.
Because that might be where the innovation lies.
Because currently the only issue is to store the methane and
That's
set
all.
pipelines.
So I'm saying that is no point again focusing on the importance of methane going to methanol, or
Right.
then you can convert it to dimethyl ether, or you see methanol can also impact on biodiesel production because after all the transesterification is done with methanol.
Yeah.
And likewise the dimethyl ether, which I can use directly in place of petrol, is a huge potential.
Yeah.
So methanol would be great, and absolutely, instead of burning it, that would be the wisest thing to do, all right? But then you have to know how to do it, and what is the bottleneck?
Yes.
Not as if those people don't know. Maybe they're just being callous and cavalier about it,
Yes.
And by the way, when people are talking about, reducing the carbon footprint, etc., these are the low-hanging fruits. Things which you're just burning, and don't burn. Make use of it. Yeah.
Yes, sir. Actually, there's a lot of research going on and it's quite recent. Like
Yeah.
it has come to light.
But I'm saying focus a bit more on that part.
Yes. Yes, sir. Hello. Am I audible?
Yeah. So this is the packaging, huh?
Yes, sir. Rethinking packaging. Yeah.
Yeah.
Yeah. So shall I start?
Yes. And I would request everybody just speak a bit louder because this is being recorded. Let the recording be nice.
Okay, okay, sir. Okay, so good morning to one and all. Our topic is rethinking packaging. So I'll be talking about the innovation, some of the few innovations in packaging. So starting with the biodegradable packaging, as we all know, has took a lot of precedent recently. So plastic, due to its slow decomposition rate, has caused widespread environmental problems. So hence, biodegradable packaging has taken precedent and was proposed as a suitable alternative for traditional plastic packaging. And some of the biodegradable packaging examples include starch, cellulose, PLA, PHB, PHA, as well as some biopolymers as well. And also, the plant-based packaging were proposed from sugarcane, coconut, hemp, as well as cornstarch, which were proposed to be replaced as an alternative for plastic packaging. Then moving on to active packaging. So food waste is a big challenge for the food industry and often incurs huge losses. And here the goal is to increase the shelf life of product and therefore it finds application in food, beverage, cosmetic, and pharmaceutical industries. And one interesting example here is to modify the atmospheric packaging, which uses
Can you
oxygen or
turn on your video?
yes, sir, I have turned it on. There seems to be some problem, I guess.
Okay.
Yeah, so as I was saying, the other interesting example is of atmospheric packaging where we can use oxygen or ethylene absorbers and moisture regulators to keep the food fresh. And another example is of releasing antimicrobial agents to prevent the bacterial growth in the product. Yeah. Yeah. Next slide. Yeah. Next. Yeah. So moving on to the recyclable packaging. So with the countries banning single-use plastics, businesses and industries have to look for materials other than plastic for product packaging to comply with the regulations. So here the example can be proposed of the post-consumer resin as a recyclable packaging material that is derived from the post-consumer waste. Then coming on to edible packaging, usually the packaging, the flowchart follows the use dispose model and so largely contribute towards the solid waste and ends up either in landfills or in water bodies. So edible packaging here poses a revolutionary alternative or innovation that addresses the challenge and closes the loop for packaging. Yeah, the good example here is of packaging made from milk protein, such as casein film around the food products, and these films are better at keeping food fresh and compared to plastic as well. Then edible spoons, straws, and other cutlery items have also been proposed for use in restaurants or cafes or ice cream parlors, with proposing an alternative compared to the plastic. Next slide, please. Yeah, and as we all know, nanotechnology is a ubiquitous field, and hence it finds application here as well. So from packaging materials to product safety, authentication, and tracking, nanotechnology has, delved into this packaging industry as well. The use of nanoparticles mixed with polymer chains was, reported to enhance barrier properties and tensile strength as well. Further, nanomaterials in packaging enables tracing and anti-counterfeiting for brands and packaging companies as well. Then, moreover, nanotechnology has also, shown a big impact on food industries by addressing the concern of food safety. Then also nano coatings are applied on the packaging surface to keep it safe from dirt, dust, and stains as well. And lastly, several types of nanosensors are useful to monitor the freshness of food and detect any chemical changes as well. Yeah, next slide, please.
Hello. Yeah, so gelatin is one such material which can be used to, just replace the plastic packaging or the films, I would say rather. So gelatin is a white or yellowish translucent lustrous solid and is a partially degraded product of collagen in animal connective tissue. Gelatin is widely used in the food, pharmaceutical, photography, and cosmetics industries due to its functional characteristics, including water binding ability, gel formation ability, and the water vapor barrier, film forming, foam forming ability, and emulsification tendency. Next slide. Hello. Yeah. So the gelatin is derived from collagen, and this is the structure of the gelatin. Next slide. Yeah. So now coming to the types of gelatin, we can broadly divide it according to its sources and according to its production process. According to sources, it is divided as type 1, type 2, and type 3 collagen derived gelatin, while the type 1 collagen derived gelatin is primarily found in connective tissues such as skin, bone, and tendon of mammals. And the type 2 and type 3 are other type of collagens from gelatin, which are found in cartilage tissues of very young skins and organs respectively. Next slide. Okay. So there is this mistake here. It's the extrusion is type twice. So the second one is mold casting.
Okay.
Yeah. Now according to the production process, they are classified as a type A gelatin products obtained by acid extraction called A gelatin, which has an isoelectric point in the range of 6 to 9, and the type B gelatin, which are alkali extracted gelatin products, and are called type B with an isoelectric point of pH 5, which can be applied to the more complex collagen found in cowhide. And compared to type A gelatin, nanoparticles in the type B gelatin have higher degree of cross-linking and therefore degrade more slowly. Yeah, types of production process. The gelatin films are majorly produced from three methods, particularly coatings, extrusion, and solution casting. Among these, the solution casting is the most widely used technique for the production of gelatin-based films. Next slide, please. Yeah. So now coming to the problem with the gelatin is that it suffers from a weak mechanical resistance and permeability to water vapor molecules, which somewhat limits the use of gelatin as a packaging material. But this problem can be solved by mixing or adding other functional materials and active ingredients to gelatin. Previously, there have been studies focused on adding proteins, carbohydrates, and polyphenols to the gelatin to improve its properties. For example, key gaze cross-linking and the addition of Zyme-reduced WS in gelatin films can improve the mechanical properties and water insolubility significantly. Another example is the addition of polyphenols improves the light resistance and antioxidant activity. And also at present, the gelatin film can be prepared by coating, casting, and extruding. But the preparation of films and means of extrusion molding is still not, not a simple matter for us. Thank you. So therefore, studies on the squeeze film is still required. That's it.
Okay. But when you're talking about gelatin, are you talking about more of the pharmaceutical type of applications? Because that is typically where they are used, no? In the capsules and things like that.
Yeah, no. So I was talking about this in the packaging of films as a film. Yeah, in the food packaging.
In the food packaging. Huh?
Yes, sir. Yeah.
So this is it goes beyond the capsules and goes into food packaging.
Yes, sir. Yes.
But there's another concern with gelatin, that because it is an animal-derived product,
yes,
there's a lot of resistance to gelatin.
Yes, sir.
Are you looking at alternatives which are close to gelatin?
Yes, actually, I read one, but it is not as good as this thing which we get from mammals. The one I was looking at was it was derived from the I think sea animals. I mean the fishes and everything, but it is not as good as the mammals. Gelatin derived from mammals.
Yeah, but then that could be an interesting area of research. That how to make it as good. Okay.
Yes.
So that's how actually one could identify some interesting opportunities for future innovation.
Yes.
Okay. Huh? All right.
That is the one you can present now. Next slide, I guess.
Good morning, everybody. I'm going to present the chemical engineer my group has chosen is Victor Mills. He is a rather more modern chemical engineer.
Just a little bit louder.
Yeah, so is it fine now?
Yeah, okay.
Better, okay. So he was born in 1897 and he died in 1997. He's an American, and in his early life he served in the World War I, and after returning from the World War he graduated from the University of Washington in a degree in chemical engineering. Following the degree, he worked at Procter and Gamble for his entire life till he retired in 1961. Next slide. So all his innovations were in the company Procter and Gamble, and he's known as the most productive technologist the company has ever seen. So this is perhaps his biggest innovation, which is the modern disposable diaper. So the story is that Procter and Gamble acquired a paper production company, and they wanted to use their new enhanced paper production capacity. And Victor Mills, who used to work in the exploratory division of the company, was tasked to somehow use this paper, and he came up with this idea. And it also invented the brand Pampers as we know it. Next slide. So this is an image from the patent that was filed by the division. It's just a schematic of what the diaper looks like. So in this case, the diaper is made of paper products. So it's just cellulose, hemicellulose, and lignin layers on top of each other. Modern diapers, as we know it, have changed, have completely changed, wherein they use hydrogels instead of papers, and they are much more effective. But he is the innovator, the first innovator. Next slide. So Victor Mills has many inventions. I'm just going through one of the most major ones. Another one is the ivory soap innovation, which is another Procter and Gamble product. So the word ivory is not really important. It's just a soap basically. But his main innovation was that the soap stock, which was previously manufactured, was manufactured in a batch process. So they used to add all these fatty acid materials. So it could be sourced from plants, animals, etc. And then they would use steam, pass it through the fatty acid, and then distill them into separate components, and you will get purer and purer stocks. So 22 carbon is a separate stock, 23 carbon, 24 carbon, etc. The problem was that it was very energy and labor intensive. Victor Mills came up with a continuous process. The schematic is on the right side. So just to very briefly explain what the innovation was, if you look at, okay, if you start from the left side, the vessel that is labeled as number 2 is where the heating material is placed. So it could be so basically any kind of combustible material is placed over there, it is heated, and then the air that is generated, the hot air, is passed through the heat exchanger at the vessel number 4. Then on top of that, at number 5, you have your fatty acid mixture, which is pumped downwards into the vessel in the middle, which is this mushroom-like structure, where the actual operation takes place. Here, the main innovation was that Victor Mills noticed that at high temperatures, you can get more efficient extraction of different fatty acids. But the problem was it would cause charring. And so Victor Mills wanted to limit the exposure of the heat to a minimum time period as much as possible. So what he did was he preheated the material in this heat exchanger over here. He passed it over to the vessel. He made sure the residence time was very little, but in that minimum time, you could extract those fatty acids which exit from the top tube over here and then pass through the condenser into the tanks at the bottom. And then the first tank at the bottom from the left side is where your fatty acid mass is continuously being recycled. So from the mushroom-like structure, any residue that remains is recycled to the tank, goes back to the heat exchanger, comes back to the mushroom-like structure, and this goes on. So this was the continuous process he developed. Next slide, please. So this is just an interesting case. Like I said, he has many inventions. So he was already an expert in soap making, and he understood all the unit operations involved there. And so P&G, Procter & Gamble, had another product, which is Duncan Hines cake mix. And so the problem they were facing is that the cake mixes turned out to be very lumpy. He wanted to be fine grainy. So what he did was, he knew that in his soap making plant, there was a milling operation involved. So what milling does is it turns any kind of bulk material into flakes, and it makes them much finer. And so he just suggested, why not use the milling operation from the soap making plant we have. And that's exactly what they did. And their cake, which wasn't selling at all before, became a huge success. Next slide. Pringles, which is a very famous snack. It was owned by Procter & Gamble then. It is owned by Kellogg's today. Now, this is also, again, very amusingly related to the soap making process as well, because Pringles is a potato snack, but the way they make it is very unique. So they finely ground the potatoes into a powder form. They mix it into a slurry. They press it into a mold, and then they bake the material. So you're getting these very fixed shape, uniform shape kind of materials, potato chips that also have dispersed in flavor. And then because they're evenly shaped, you can package them such that it's such that you have minimum air inside it. So eventually it helps in storage and distribution as well. So the point was that, how does soap factor into here? The soap making process also uses the slurry system. Then it's transferred to a mold and then baked. So that's how the whole idea of Pringles emerged, basically. So I'll show you the manufacturing process in a second. In the next slide, please. So this is a schematic from the patent of Pringles filed in 1976, if I remember. So if you start from the top right, at the top right, there's a conveyor belt that transfers the dough, which is basically a starch, potato grains, and everything, down to the left side, where there's a cutter labeled as 15 over here. And that cutter cuts these hyperbolic curved shape dough and then transfers them onto these knife-like structures you see in this kind of assembly line. And those knife-like structures are basically molds. So this cutter transfers the dough onto those molds, and then those molds have two. So there are two mold halves, and once the dough is transferred to the mold, the mold half closes, and then this mold then travels throughout the circle. It ends up near this oil bath you will see at the bottom right, and then in the oil bath it is fried, and then it returns back, and then it is disengaged at the top at the left side of this conveyor belt, and then further processing such as salting and then sprinkling with other spices is done. So these are just some innovations of Victor Mills. It shows you in some innovations he has done as an employee in the exploratory division's product. So I would say he really got a lot of leeway to do creative things and innovative things over here, because that's what the division mandated, to try new products.
Very nice. Actually, Procter & Gamble have been very well known for shifting some kind of core competencies that they develop across the company into different product areas. They've been very good at it. What I will do is, if possible, I'll send you a link to an interview with the vice president of their research. He's not there anymore, Dr. Shekhar Mitra, who happened to be my classmate in IIT Kanpur. And you will see from that interview how they continue to do this, very similar to Bosch, and BASF, how they move knowledge across boundaries, from one area into another. So that's something, it's a very wonderful lesson to learn from Procter & Gamble. and victor minerals. Okay, thank you.
Thank you, sir.
Next.
Thank you, sir.
So, good morning, sir. So, our idea to be presented was about the less energy intensive advanced separation processes. Next slide, please. Among all the separation processes, as we see, the distillation and evaporation are the major, most energy intensive separation processes. Despite this fact, they have several advantages over other separation processes and hence are widely used in the industry. Therefore, the challenge for today is to capture the advantages from the other separation processes and try to integrate with them with the current distillation and evaporation techniques. So what are the barriers that are avoiding us from replacing the distillation and evaporation? Firstly, there is insufficient selectivity by material agents, be it membrane separations or extractions, etc. But the selectivity has been very low as compared to distillation. Second is the inability of the material agents to maintain the performance under very harsh conditions such as high temperature, pressure, and pH values. The next is inadequate throughput by material agents for reasonable economics. So changing equipment and all costs very high, and therefore it is very difficult for replacement. And the final is insufficient economic incentive to consider the improved process technology as replacement technology. We can see ahead why this is a barrier. Next slide, please. So now, how to overcome this problem? So firstly, the chemicals and petroleum refining are very mature and highly capital intensive and competitive industries. They have a very long economic life of the existing facilities, which are hindering the development of other economic large-scale non-conventional separation technologies. Now, in order to overcome the market acceptance and the economic barriers we mentioned, new and advanced separation materials must be developed with very high superior performance as compared to the existing technologies. Next slide. So the first technology we need to discuss is about distillation. As we know, distillation cost almost half of the energy consumption required by the separation processes together. So what are the alternatives for distillation? Firstly, we are going to talk about extraction and absorption. Solvent extraction and absorption have been traditionally been practiced in the industry, but they have been considered as relatively large equipment size requiring large solvent and absorbent inventories. So in order to reduce this factor, research has to be focused on producing new solvents and absorbents with high selectivity and yield, and also with durability to withstand harsh environments. Only then this technology will be competitive to distillation technology. Next slide. So here are a few examples of what can be developed, what has been developed in extraction and absorption in order to be it more competitive to distillation. Firstly, we have pipe bonding materials such as previous slide, Rajesh. So firstly, we have the pipe bonding materials such as cuprous ions and silver ions. These they have extremely high selectivity for olefins such as ethylene and propylene, as they form complex compounds with these compounds. Also, their solutions are regenerated without using distillation, so they are very effective. And another distillation based separation might include crown ethers, use of crown ethers and their derivatives, which can act as molecular sieve cavities for certain compounds. So here also they can be used instead of distillation. Also there is example of an equipment like use of rotating contactors Here, use of rotating contactors reduces the solvent inventory in the extractor by 1 or 2 magnitudes as compared to the normal ones. Next slide. Now, the second alternative for distillation is membranes. Now we know that the membranes are extensively being used and being researched on in the industry. But the greatest limitation to the application of membrane separation technology is the lack of selectivity and the narrow range of operating conditions. And also the costs are very high when it comes to large scale applications. So still we in order to consider membranes for as a replacement, we need some particular properties from membrane materials, which include permeability, selectivity, durability, resistance, impact strength, and flexibility. So cost reduction is also achieved by converting from plate and frame systems to spiral wound or hollow fiber modules, as they have more area of contact. Next slide. So basically 2 areas of research which are going on extensively. They are in inorganic membranes and composite membranes. So inorganic membranes include ceramic, nanostructured membranes, zeolite membranes. These membranes are not only considered for liquid-liquid separations, but also for gas component separations as well, and in molecular using molecular sieving. Next is composite membranes. Inorganic and organic composite membranes are have been developed for low temperature applications. Next slide. The third alternative for distillation we can see is hybrid systems. These new hybrid systems include field enhanced distillation, reactive and extractive distillation, and membrane reactors. Hybrid systems are basically a combination of 2 systems, out of which one is distillation while the other is some other unit operation. Here it requires the development of mass separating agents and the equipment designs also to incorporate the separating agents into distillation equipment itself. Next slide. So first example is pervaporation. This pervaporation is commonly known as membrane distillation, and this is an important separation process considering the rapid growth of ethanol as a fuel additive. It is used to particularly separate ethanol water separations. Then next is the distillation adsorption hybrid process, in which we have a rough separation with distillation, which is followed by polishing with adsorption. The potential energy savings for such systems are very high, and they are considered to be of effective replacement for distillation technology. Next slide. So the second technology is evaporation, which also accounts for much higher amount of energy. So for the alternatives to evaporation include membranes. As we have discussed earlier, the properties required for membranes are similar: durability, selectivity, resistance to fouling, etc. But the implementation of these hybrid systems. Hello.
Yeah.
Yes. So I guess Rajesh mic. So,
Oh, sorry, there was some error. I thought sharing stopped. You can see the screen.
Yeah. I
okay.
can see. Okay.
This slide is correct.
Yes.
Sorry.
So implementation of hybrid systems such as combining membranes with evaporation operation. This can be more practical and economical rather than completely using membranes instead of evaporation. Another option is to couple electrolysis with evaporation as well. Next slide. So another alternative for evaporation is advanced filtration. So in advanced filtration techniques such as cross-flow filtration can be used for as an alternative to evaporation. Now, while we consider these techniques, there should be improvement in separating media and also the changes in the equipment design as well, in order to make the technology economically competitive to evaporation. Also, the other equipment such as vibrating disc, ultrasonics can also be used in order to make the technology more competitive. Next slide. So Roshali will explain about the chemical engineer, Henry Moison.
Okay. Now, most of these separation processes that you talked about with membranes, were they all primarily aqueous systems?
Yes, sir, liquid ones.
Yeah, but aqueous, right? You know, the thing
yes, sir.
is that there are also membranes which have been developed which you can use for entirely organic systems.
Yes, sir.
So like these are typically polyimide type of membranes, and you know, that is a potentially very promising area which is relatively not being worked on.
Yes, sir.
Is look at all kinds of non-aqueous systems and distillation processes in those and try to replace those with more energy efficient alternatives.
Yes, sir. Yes, sir.
Okay. Okay, good.
Sir, can I start?
Yes, please.
Yes, sir. So I will be discussing about the Henry Moison. So basically, his biography is summarized here. He was born in Paris in 1852. He attended School of Pharmacy and he completed his PhD on cyanogen chemistry and later joined the School of Pharmacy as an assistant lecturer. Next. Now, throughout his career, he did some notable work and mostly in the domain of inorganic chemistry, which is briefly summarized here as his major inventions include fluorine chemistry, meteorite fragment found in the meteor crater, and invention of electric furnace. Next. Yeah, so fluorine isolation was a signature work of Henry Moison. Now, he initially worked in the biology domain on the interchange of oxygen and CO2 in the plant leaves, and later he shifted his focus in inorganic chemistry, where his early work was on the iron oxide and chromous salts, and in 1884 he started working on the fluorine. He prepared some organic and phosphorus derivatives, and in 1885, he discovered that if potassium difluoride is dissolved into liquid hydrogen fluoride at certain strength, the mixture remains in the liquid phase, and in sub-zero temperature, the solution can be electrolyzed. So later, he tried to electrolyze the solution in order to isolate the fluorine, but initially he ruined the platinum equipment which he was using because he tried to electrolyze the solution at higher temperature. So later he tried to carry out the same experiment as minus 50 degrees Celsius. And finally, on 26 June 1886, when he passed the powerful electric current through the solution of hydrogen fluoride and molten potassium fluoride electrolyte, he noticed a green yellowish gas at the end, which was basically fluorine. So he was able to isolate the gas and it allowed for its subsequent collection, observation, and its use in the other experiments. So basically, this is the root of the fluorine synthesis from the electrolysis of potassium fluoride, which is shown as the mechanism. And on the side by, there is a schematic of electrolysis reaction where the fluorine is released at the anode. Next slide. Also, Moison later theorized that we can produce a synthetic diamond by crystallizing the cheaper form of carbon, such as charcoal, under the pressure of molten iron. So he said to prove that experimentally, and in 1892 he developed electric arc furnace, which could attain the temperature up to 3,500 degrees. And he finally produced some few pieces of stones which were shiny and tough as diamonds, but whether they were diamonds or not was very much debatable. And later in 1893, he discovered silicon carbide while examining the rock sample from the meteorite. And also he synthesized various minerals using electric arc furnace. Next slide. Yeah, so the furnace, which was developed in 1892, was used by Moissan to volatilize many substances which were initially thought to be infusible, which cannot be melted. And also he synthesized various chemicals using the same. And he discovered many new compounds such as carbides and borides. Also, his close study of the carbides and their reaction led to one theory in which he said that in some cases petroleum may be formed by underground reaction between carbides and water. So later he proceeded in order to produce acetylene using calcium carbide. Now the furnace which he produced was in the laboratory can attain the temperature around 3000 to 3500 degrees, and industrially it can attain the temperature around 1800 or 2000 degrees. And the furnace was basically a limestone blocks with the hollow cavity where the carbon rods were used as the electrode. And when the electric current of the few hundred ampere were put down, the energetic stream is produced, and which will produce the temperature of 1000 of degrees. Next slide. Now, the significant contribution of Moissan is reviewed here. Now, the first one is the method by which he isolated the fluorine is the same method which is utilized even today for the commercial synthesis of the fluorine gas, which is the electrolysis of potassium fluoride. And also, owing to the electric furnace, Henry uncovered various wide range of boride and carbide, like silicon and tungsten carbide, which have a wide application in the drill, cutting, or as abrasives using the electric furnace. And the Moissan arc furnaces are also the backbone of the ceramic manufacturing. And he devised a commercially profitable method for producing acetylene, where basically he mixed the limestone and coal at a high temperature to create the calcium carbide, and later he combined it with the water, and which is the basic process of the acetylene manufacturing. Next slide. And finally, his work was recognized worldwide, and he received the appreciation through the several awards. Henry Moissan was awarded a Nobel Prize in 1906 for his remarkable work in fluorine isolation and arc furnace development. And also, he received various awards like Davy Medal by Royal Society of London and Elliott Crescent Medal by Franklin Institute, etc. So that's it from me.
Okay, thank you. I hope you can, also see the relationship between Hall Herold's work, where he dissolved alumina in cryolite and how KHF2 was dissolved in HF. So there are analogies, although one is a high temperature process and one is a sub-zero process. So these are very interesting. And second, also that look, he developed the electric arc furnace really to make diamond.
Yes, yes, sir.
That was the
his only
driving
process
force.
was to prove his theory that he can produce diamond.
Yeah, I mean, he was helping to make diamond, and in the process, you just see what happened. I mean, the number of things which came out of the fact that he could make the electric arc furnace. So if you are really chasing a passion, take it to its logical conclusion, and if things are not available, create those, okay, which will make it happen. Very nice. Okay.
Thank you,
Now time is up. So what should we do, Rajesh?
You can hear me now?
Yeah, I can hear you.
So I'm Abhinav Patil, and I'll be presenting the paper industry, like alternative sources for making paper. So as we know, the paper industry represents like 2% of the world commerce, and its demand has been increasing every day. Paper still is in the main form of communication among people, especially in the educational field. It has an infinite number of industrial uses, amongst which we can mention those related with packing and healthcare. Now, talking about the hazards, like 40% of the world's commercially cut timber is used for the production of the paper. Pulpwood plantations and mills endangered natural habitats. over 30 million acres of forests are destroyed annually for this paper. The pulp and paper industry is partly to blame for the endangerment of some species that live in the forest. The process of making paper is damaging to the environment from beginning to the end. It starts off with a tree being cut down and it's being burned, emitting carbon dioxide into the atmosphere. So and also an A4 paper requires 10 liters of water per sheet. Most of the materials in landfills are made of paper. When paper rots, it emits methane, greenhouse gases. When it is burned or decomposed, like carbon dioxide is emitted. Now, chopping down trees decreases the amount of oxygen in the ecosystem and thus adversely affects the other life forms. And there's also the continuous use of chlorine as a bleach. Now, here are some alternative sources. First, the eco papers. So, eco papers are agro-industrial fibers come from the waste of the processing common agricultural industrial products. Eco papers specifically come with the waste of bananas, mangoes, coffee, and tobacco. Research is currently involved in studying new fibers from pineapple, orange, and palm trees. So about the banana paper. So banana paper is used in two different senses to refer a paper made from the bark of the banana plant, mainly used for artistic purposes, or paper made from banana fiber obtained from an industrialized process from the stems and the non-utilized fruits. This paper can either be handmade or made by industrialized handmade machines. The banana agro industry processes each year 42 million tons of bananas with 20,000 square kilometers plant. The industry generates numerous wastes, such as the plastic that wraps the bananas, plastic cords to tie up the wrapping, damaged bananas and the stems. The stems are composed of like 92% water, 3% resins, and 2% glucose, and the rest is vegetable fiber. So this causes this particular composition makes it to decompose with the solid component not getting destroyed. This causes a severe impact on the surrounding ecosystems. The detriment of rivers and underground waters, also the massive reproduction of flies and nauseous smells. Agro-industrial fibers come from the waste of processing common agricultural products. And the mango paper is a slight variant of kiri paper and is handmade. So kiri paper are made with the help of long kozo fibers and mulberry barks. The same ingredients are used when making mango paper, but instead of mulberry barks, kozo fibers are included in the proportion of 60:40. These papers are made in abundance in Thailand and India and are light in weight, semi-transparent in nature, and are very delicate. They are also available in variety of colors, but are usually made in variations of yellow and green. So now, talking about the buggies and bamboo. The buggies is now extensively used to make various commercial products. The material is ideal for the use of depithing process removal, that is the removal of the pith portion of the stem. The pulp can be used to make newspapers, printing papers, tissues, packing boxes, etc. And just like wood pulp, products are made from bamboo and can be easily recycled. The quality of the bamboo paper used is comparable to the paper wood pulp in terms of strength, brightness, and printability. Now, papers can also be made from old t-shirts. The cotton extracted from the fabrics produces a particularly strong type of paper and is combined with other fibers to make paper for legal documents that need to last, or banknotes. It also can be made from the feces of the herbivores. The American company, this poo-poo paper, sells paper made from the excrement of cows, donkeys, horses, elephants, and even pandas. Herbivores' feces are rich in fibers derived from the plants and fruit these animals eat. By using a cleaning and filtering process, it is possible to make a superb and completely odorless paper out of this. Some believe that this technique could help tackle the serious problems of managing the waste product produced in the raising of the animals. Now, The papers can also be made from stones. So stone paper is manufactured with calcium carbonate bonded with small amount of high density polyethylene resins, also known as the limestone paper. The material is quite durable, yet not biodegradable. However, it is photodegradable and compostable. The paper can be recycled into the same mineral-rich paper again. The paper works well with solid ink and inkjet printers, but not too well with high temperature laser printers. So it can be used, like widely used for making stationery, books, magazines, wallpapers, packaging, etc. Now, these are the advantages, like it's a attractive product, it's original, and it's like shows hours of dedication, it's environmental friendly, and it's good, it has good quality, and it's elegant. So now focusing on the eco part, by utilizing agricultural waste for the paper production like banana stem, paddy straw, wheat straw, areca nut, husk, but mainly focusing on obtaining the banana paper. So what is the current situation? Like after harvesting, billions of tons of billions of tons of stems and leaves are dumped away on the field burns, in the rivers and natural drains, and even burning them, which causes environmental issues. So why do we select the banana plant? Because like banana is one of the important fruit crops grown almost in every state of India, like in many seasons, also in various different regions. Apart from fruit, it generates huge quantity of biomass, like from the stems and leaves, etc., and average about 60 to 80 tons per harvest in stem alone. So this is how the banana paper is produced. Like first it's chipped, and then it's digested, and then pulping and washing, and then it is spread and rolled to form a paper. These are the advantages, like that banana stem waste disposal problem can be consequently in the environment, pollution issues can be solved. It will be a source of income for farmers. Wood consumption for paper production will be reduced. New industrial setups of banana stem processing will provide new job opportunities even. Thank you, sir. This is the end of the first idea part.
Yeah, I think it's very interesting. Only thing is, it looks like you'll get more customized paper. You know, these mass production papers like for newspaper and things like that, you know.
Yes.
Whether these sorts of paper will be useful for that, I don't know. But it will probably be quite all right for drawing books, you know, painters, you know, artists.
Yes, sir. That
I
will
think
save millions of trees. So
yeah, I think you need to really figure out, and this paper would be biodegradable, right?
Yes, sir.
Huh? Yeah,
Yes, sir.
I mean, I think it's a very good idea. What you should find out is what are the weaknesses of this paper, you know, for mass production. You know?
Yes, sir. Yes.
Okay, and mass consumption. That I think is something that you need to figure out. Like, for example, can one make toilet paper with this? Because that's one of the biggest applications of paper. You know?
Yes, sir. Yes, sir. It can be formed. Yes, sir. With
It can
using
be?
like the old t-shirts and all, with that
Yeah.
we can make it. Yes, sir.
Yeah, just, you know, about a week back, they were showing a documentary on BBC where apparently Peru is the country where apparently, you know, all the used clothes and things like that are all dumped in Peru. You know.
Yes, sir. Yes.
And then from that, they pick out clothes which are saleable and they make money from that. And the rest of it is just littering the whole country. You know? They were showing it about a week back. So, you know, if they could start some industries like this, that would be interesting.
Yes, sir. Yes. Yeah, sure.
No, I think clothes are a bit difficult because they come in so many colors.
Yes, sir. Yes, sir. The
So that
cotton
will
is
be a
well.
problem.
Yes, sir.
Whereas these things are okay, this banana or mango, etc., because they would be more monochromatic. You know?
Yes, sir. So that's why I focus more on the banana part. So like it helps the farmers to like to get, and also provide job opportunities for different persons too.
Yeah. Yeah, I think it's very interesting.
Yes, sir. Yes.
Okay. all the people who make presentations just say tell your name first, huh? Because what's happening is, it's getting a bit blocked off in the presentation. Maybe I should have actually shown the presentation. Then this problem may not have arisen. Okay, because I'm the host. Rajesh is showing the presentation and you are presenting. So
Yes,
that's why
sir.
it's creating a bit of a
So I'm Abhinav Patel.
Abhinav. Okay.
Yes, sir. And I would like Mayur Kulmete to present now proceed further.
Okay, fine.
Yes, sir. So from here, I'll be talking about innovation made by engineers, which we have chose to discuss about. So I will be talking here about Charles Edward Howard and Norbert Relix. So for whole humankind, they had made the life of humankind very sweet by improving the sugar refining process. And also they both are being been recognized as the two of the most significant figures in the prehistory of chemical engineering. Next slide. It is said that harvested cane was processed at a rate of 1 slave life per 2 tons of sugar, cause the production of sugar, refined sugar, was very dangerous. That the slave or worker, whoever were working in the industry or factory, they have to face lot of hazards and challenges, as at that time all the work were done by manually, no machineries were there, so they have to hold all those hot equipment with their hands and transfer those hot liquid from one container to the another container. And it was very common at that time in sugar refining of fire hazard. So next slide. So Edward Charles Howard, he was a British chemist and also described as the first chemical engineer of any emissions. Uh, Also, he was a fellow of the Royal Society and awarded with a Copley medal for his work on mercury, where he prepared mercury fulminates and described about its detonating power. And also he had made some contribution in cosmics. Next. So the patent he had known for his that vacuum pan, where this equipment has replaced the process where open kettle were used for making refined sugar. After this equipment invention, those kettles were known as Jamaica train, and those were replaced with this vacuum pan, where the temperature can be lowered to the successive pans for getting the thicker syrup thicker syrup, and it prevent the caramelization and burning of sugar. And using this equipment also, we were getting a purified solution, means impurities of all those bagages which would be remaining, those were removed, and clear crystal sugar was getting, which was a improved product. Next slide. And after that, the Norbert Relix, using previous equipment, he made some changes. He was also a physicist, mechanics and engineering. He was excelled in these fields, and as his father was working in the sugar refinery, refining sugar industry, so he knew what all challenges were there. So he decided to use his knowledge and design some instrument that will be easy for workers to use. So he had constructed a triple large effect evaporator, which was Howard's earlier work. Next slide. Here in this evaporator, he used the heat of vaporization from the steam in the first evaporator, to hit the more concentrated sugar solution, which was in the second evaporator. And then similarly, for the next evaporators, where in the successive evaporator, the temperature required were less, as those were conducting in the vacuum, and elevated pressure reduced as the elevated pressure was reduced of the sugar solution. And next slide.
Elevated pressure reduced means more vacuum.
Yeah, sir, sorry. That vacuum means more vacuum was there in the successive equipments. Next slide. And then firstly, he was his patent was not accepted, although it was giving a good quality of sugar and reducing cost, fuel cost, and giving good revenue. But because of the civil war was going on and racial codes, his plans were rejected. So he returned to France. Next slide. And then he worked with the engineers in France, and in 1881 he came back with a multi-stage system of sugar beet processing and for sugarcane processing, which are nowadays still used in a sugar refining process. Next slide. The invention is is operating across a range of processes industries, even in the space shuttle also. And because of this invention, the process of producing refined sugar became less dangerous and also cost efficient, and it benefited the human mankind. Thank you. So it was all.
Thank you. There are two people who presented, right?
Yes, sir. So Shantanu also contributed, but he had some network issues. So I chose to take his part.
Oh, I see. So Shantanu participated. Huh?
Yes, sir. Yes, sir. He contributed well. Yes.
Okay. Okay. All right. And could you dig out any additional information, because I found that you have really taken most of the stuff from the chemical engineers who changed the world. But I was just wondering whether you could get any other or you try to access any other source of information. Like, did you ever try to have a look at their patents or anything?
No, sir. I had tried other sources, but there I was not getting the work where they both have contributed together. Means in a field.
Okay, fine.
We are presenting the Waste to Wealth initiative. So my it's Advay Shirwadkar, and my partner is Swapnil Gudve. So let's start with defining waste. So a crude definition of waste can be given as anything that which cannot be used, is just at any period, is waste. But over the time, the definition changed. It got changed due to the existing and practicing technologies. It is It is the innovation in the technology that has the potential to change the definition of the waste from time to time. So, for example, about 2 to 300 years ago, the bagasse and the cow dung or the animal dung was used for brick fire, like as a fuel for cooking food. But over the period, the technologies grew and improved. Now the material is used as a feed for obtaining or producing the building block chemicals like methane, methanol, water, syngas, etc. So over the time, the waste, the definition of the waste had changed drastically, and the waste which is produced by a single process is minimized. So there are various types of waste like municipal waste, biological waste, which is hazardous, radioactive waste, and agricultural waste, and many more. But let's talk to a municipal level. Before that, these are the statistics of the whole world, which produce the waste per person. Like it is USA and Canada which account for approximately 1.5 kilogram waste per person, whereas the underdeveloped nations and the developing nations account for less than 1 kilogram per person. So starting with the treatment of municipal waste, the waste can be treated in various ways. Like the waste can be treated to waste to energy plant to obtain energy, whereas the ash or the leftover is used for landfilling. The mechanical or biological treatment, like the sewage water, is generally subjected to mechanical and biological treatment, and the waste residue is used for landfilling. The material recovery facility, in this process the material undergoes certain reactions to obtain a value added product, and the residue is again used for landfilling. And the organic recovery facility, here the organic material present in the sewage water or any other kind of waste is recovered, and the residue is dumped or used in landfilling. So stating about the current waste to wealth initiative, it is Adidas who started who collabed with Parley in order to start using the polymer, the ocean polymers, in making its shoes. Like it uses about 75% of the recycled plastic in its shoes. Like in 2019, they had manufactured 11 million pairs of shoes, which is double what it produced in 2018. The whole process utilizes approximately 2,800 tons of plastic from ocean waste. The plastic used generally is of PET, polyethylene terephthalate. The main advantage was the process utilizes less water than what it utilizes for making a whole new stuff from from all the raw materials. And it also recycles the existing plastic from the ocean waste. Second initiative is the Indian initiative. It's like it's protoprint. It is a Pune based startup wherein it collects the plastic filaments present in the plastic filaments that are found on various beach. The small pieces which are not used for which cannot be used for any other process is thus collected, separated, and can be used for 3D printing. The plastic is processed, and small balls are made from it, which is processed to make make any other equipment, any other part through 3D printing. Yep. Swapnil.
Good afternoon, sir. My name is Swapnil Guve, and I'll be talking about another Indian startup.
Okay.
It's called GPS Renewables. GPS Renewables is a Bangalore-based enterprise that is solving the urban organic waste management problem in an economical and environmentally clean way. It was founded by Mainak Chakravarti and Shri Krishna Sankar, and their company is working on thumb rule of zero wastage policy. It is turning all the kitchen and organic waste into biogas, which has been around in India for a long time, but its installation have traditionally not been taken off because of poor awareness and because of its cost issues. The company launched a pilot project named Bio Urja, which is a compact plug and play system that uses that so that users can install anywhere with minimal civil work, and it is perfect for bulk generations of biodegradable waste. The system has proven to be effective since 2013, and the processes around 600 kgs of kitchen waste every single day. The company has now expanded beyond India into Bangladesh, Malaysia, and even Sri Lanka. Next slide. So another startup is about cigars. It's called No More Butts. This startup collects and recycles cigarette waste and even pays you for smoking cigarettes, although it is harmful. But it is harmful even when it is disposed of. Cigarette butts can take anywhere between 18 months to 10 years to fully decompose. The cigarette butts discarded after smoking is one of the most littered items in the world today, and therefore it is an environmental hazard. No More Butts is a Noida-based company, and another company called Code is recycling all kinds of cigarette waste and trying to tackle this problem. Vishal Kant and Naman Gupta are the two friends in their 20s started this startup, and the company pays around 700 rupees for every kg of cigarette waste and rupees 80 for every 100 grams. Their customers are people who smoke as well as the dealers which sell cigarettes. I'll just brief up about the process. It all starts with the beach. Parley and his partners collect trash from the coastal areas like Maldives. The waste is then sorted and the recovered plastic is sent to an Adidas processing plant. Adidas uses plastic bottles that contain PET, and it's something Adidas can't use. Like caps and rings, those get sent to normal recycling facilities. The processing plant crushes, washes, and dehydrates the waste, leaving nothing but small plastic flakes. These flakes are heated, dried, cooled, and then cut into small resin pellets. Normally, polyester is made of petroleum, but Adidas melts these pellets to create a filament, which they spun into what they call ocean plastic. And they have branded it as Parley filament or Parley fiber, which is a form of polyester yarn. Adidas uses ocean plastic to form the upper parts of shoes and clothing like jerseys. Each item in Parley collection is made from at least 75% of intercepted marine trash, and they still meet the same performance and comfort standards of Adidas other shoes and performance gear. Recycled polyester uses less water and fewer chemicals and helps prevent plastic pollution. Okay. Now about the scientists who changed chemical engineering. I'll be talking about Victor Mills, who changed the world with his ideas such as Pringles, and which the Pringles is a well-known company and which owes a lot to soap production process, and of course the idea of using shredded absorbent paper in a nappy that could be thrown away after use, which later gave birth to the well-known company Pampers. So Victor Mills, as Vic Mills, as he is more commonly known, was a legend in his lifetime. He's a chemical engineer graduate from the University of Washington. He spent his career working for consumer products giant Procter and Gamble (P&G) and was instrumental in developing some of the P&G's most iconic products. Over the course of his 35 years career with P&G, Mills became the head of exploratory product division, which allowed him to produce and improve a multitude of existing processes and products and develop a whole lot more. It drastically cut the production of ivory soap, stopped the oil from separating out of peanut butter, and solved a particularly annoying problem with Duncan Hine cake mixes. The Duncan Hine cake mixes suffered a problem which caused their soaps to clump. Mills also developed the production concept for Pringles crisps, which are without it, Pringles would neither be in uniform shape and neither would they stack in the packaging. However, the innovation for which most remember him is the world's first commercially successful disposable napkin, Pampers. Next slide. Okay, thank you. Early life. I'll be talking about his early life. Mills was born in 1897 in Nebraska. He served with the U.S. Navy during World War I and then moved to Hawaii, where he was worked as a welder. He was initially planned to study civil engineering, but he pursued chemical engineering at University of Washington, where he met another chemical engineer who changed the world with his idea for developing PVC and certain synthetic rubbers. His name was Waldo Simon, who is best remembered for developing PVC and certain synthetic rubber. When Simon ran into difficulties with the synthetic rubber he was working on, he approached Mills. Mills was able to produce a special blend of ivory soap flakes that helped Simon solve the problem. Indeed, ivory soap was one of the first products Mills worked on after joining P&G in 1926 as one of their first ever chemical engineers at the company. The challenge he faced was to reduce the production cost. At that time, soap was produced using a batch process, which was time and labor intensive. It was Mills who invented the continuous hydrolyzer process that enabled the continuous production of base soap stock. He is also credited with developing a continuous hydrogenation process for the production of edible oils. And what separates Mills from other scientists is that his ability to transfer innovation from one product family to another. When he was asked to work on P&G's cake mixtures, the cakes did not always mix properly and turned out to be lumpy. Mill's solution was to take the kind of machines used to mill soaps to very fine flakes and run cake mixture through them. It worked, and new finer cake mixtures no longer clumped, and Duncan Hines mixture turned from a problem brand into the US market leader within the short span of 3 years. The concept Pringles is based on the same principle, to which Mills was a chief contributor, equally owes a lot to the soap production process he invented. Unlike regular crisps, which are cut from potatoes and fried in whatever shape they happen to have grown, Pringles were really different. Pringles are made from finely ground potatoes and have been mixed into a slurry, pressed, and then baked. This gives them a unique shape, facilitates the even distribution of flavorings, and also makes them for a denser product, which equates to a fewer loads and more efficient distribution process. Next slide. The early napkins were very basic, essentially rectangular pads of tissue paper with a rayon liner and polyethylene outer. Mill's crowning glory, the disposable napkin, came fairly late in his career. Mills was over 60 years old, and even he was asked to think up for some new and exciting ways to use paper. Recently, P&G had developed a partnership and acquired Charmin Paper Company and needed new products to get good use of its newly acquired paper production. Mills, it's a funny story. Mills, who had recently become a grandfather for the first time, he always hated washing napkins. Given the desire for a new product using this paper, Mills came up with the brilliant idea of using shredded absorbent paper in a napkin that could be thrown away after use. Pediatricians also liked the idea because napkin rash was caused by white skin, and this was a real problem. The exploratory division at P&G swung into action. The task was to find a product with sufficient absorption for the task, which didn't leak and kept baby skin reasonably dry. One of the first actions was to visit a toy shop and procure a realistic urinating doll popular during 1950s. This doll helped the engineers with the early product development, and the further testing of the product was tested on the grandchildren of Mills. Following product tests in Rochester, New York in 1959, for which 37,000 napkins had to be hand-sewn, Pampers disposable napkins were commercially launched in Illinois in 1961, the year Mills retired. And now Advai will tell you about more about this.
The advancements were the napkins were more user friendly, economic. The patent was filed on the name of P&G. It's thick. The napkin was thin and environmental friendly. Further product development soon made the napkin more user friendly. For example, by replacing the pin with adhesive tapes and improving the fit and therefore leak resistant around the leg. The advances in the production process soon brought down the prices. Soon the demand also soared through the demand. Soon the demands also hiked up. The Pampers across. However, Mill was unable to obtain a sufficient supply to use the nappies on his granddaughter, who was born in 1962. The patent was used. The patent for using super absorbent polymers in nappies was independently filed in 1966 by both Johnson and Johnson and Billie Jean Harper of Dow Chemicals. Super absorbers work like a lattice that expands to absorb liquid, and they can hold up to 300 times their weight in water. The polymer increases the absorbent power of the nappies, yet made them more thinner. It was a significant advantage because it allowed shops to display more and more nappies until then available shelf space have been a severe bottleneck. In addition, super absorbents made for a better product. Until then, the skin wetting still proved to be a problem because the paper nappies, once they are wet, allow a certain amount of moisture to soak back through the surface. This is particularly the problematic when the nappies come under pressure. A baby sitting or a baby sitting on a bottom exerts as much as 5 kilopascals of pressure on the nappy core. Thus, replacing the thick paper with super absorbent found very innovative during that period, and thus it helped change the world, or it helped change few things.
Okay. Over now?
Yes, sir.
So we are going to talk about inherent safety, its principles, and we will also discuss a case study wherein we'll apply the principles of inherent safety so that they are understood better. And the scientist that we are going to talk about today is Trevor Kletz, who's known as the father of inherent safety. Next. It is defined that an inherently safe plant relies on chemistry and physics to prevent accidents rather than on control systems, interlocks, redundancy, and special operating procedures to prevent accidents. Next. So Trevor Kletz, in his book called Process Plants, explained what inherent safety was, and he based that ideology on 4 key principles which can easily be described through 4 keywords. The first one being minimize, where he said that it was essential to reduce inventory of hazardous chemicals in a plant so that if there was an outbreak of such chemicals, it could be controlled and would not lead to catastrophes. The second keyword he used was substitute, where he said that toxic or hazardous volatile solvents should be replaced with less toxic reagents or solvents. The third one was moderate, where he explained that it was essential that the operating conditions in a plant be moderate in terms of the temperatures and pressures. Also, hazardous materials that are used can be diluted, and vacuum can be used to reduce boiling points of chemicals. The fourth keyword was simplify, where he explained that the complexity of a plant can be reduced to a great extent, and this can be done by following simple principles such as having neat piping systems, properly labeling pipes and equipments for simple identification of them, and also using control panels that are easy to understand. Next.
Our idea, we are going to explain our idea through a case study. We have taken a particular accident and we have applied these 4 principles of inherent safety to this accident, and we have explained how it could have been avoided and the extent to which the damage was done can be minimized by following those 4 principles.
So we have taken the accident of the sugar dust explosion and consequent fire at the Imperial Sugar Company in Georgia. In this accident, what happened was
You're
the
fading a
conveyor
bit.
belt which was
Just
carrying sugar. Sorry.
no, I'm saying you're fading. Your voice is fading.
Oh, sorry, sir. So I was saying that the accident which we have taken is the sugar dust explosion in Georgia, in which a refinery which converted granulated raw sugar cane to granulated sugar was transporting the raw sugar using screw and belt conveyors. And below one of the sugar silos, the sugar dust, it accumulated to such an extent that an explosion happened, and that led to a consequent fire. And because of the during the explosion, the water pipes and all the sprinkler systems were also ruptured, which is why the fire could not be further mitigated. And during this accident, almost 14 workers were killed and 36 were injured. Now we have analyzed accident using those four principles of inherent safety, and we have given suggestions as to how it could have been avoided. So along the principle of moderation, the sugar dust consisted of very fine particles which got accumulated and led to the explosion. So this reaction could have been controlled if we had used particles having surface area which was larger than the sugar dust particles. So we could have used pellets or slurries also. Process conditions could
No, but
also have.
how is the dust forming in the first place?
Sir, the sugar, when it is getting transported, it inherently has some amount of dust, but that dust actually is usually less than the concentration which is acceptable. But over here, it got accumulated to such an extent that the explosion happened.
Right. So are you saying that they actually failed in the quality control?
Yes, sir.
Right? They did not monitor it properly.
Yes, sir.
Okay. So, but where is the moderating then?
Sir, the surface area of the sugar which was being transported.
No, I understand. But what I'm saying is that if there is always going to be some dust which is formed,
yes,
right?
Sir.
And if it is unavoidable, then how exactly will you moderate that?
So using the storage conditions, because at a particular temperature and certain humidity, that dust starts reacting with the environment around it, and that was what led to the explosion, according to the research paper which we read. So they have said that if the temperature had been less than the particular temperature at which ignition happens, then the explosion could have been avoided. So if the storage conditions of the, not the storage conditions, but the operating conditions of the steel conveyor belt, if it had been moderate, then it would have been avoided. And the third suggestion which was there was we could have added inert solids to it, because in previous accidents where dust explosion has happened, the corrective measures were taken by adding some silica beads which improve the flow and prevent dust cloud formation, and therefore the mixture remains stable and the explosion can be prevented. The next is simplify. It was also noticed that because of the presence of a certain exhaust duct at the exit of the ruptured disc, the flow of the exhaust, the dust particles could not easily escape after the allowable pressure was reached. So if we could have removed this duct, then the flow would have been better. The flow rate would have been such that the accumulation of the dust particles in the conveyor belt could have been reduced, and the explosion could have been stopped. Snehal will take it from here.
Yes, so the next principle is minimize. So first of all, we could have minimized the volume of dust clouds that generated at the transport points. So that could have been achieved by changing the equipment design and by achieving mass flow rather than funnel flow, as funnel flow generates dust clouds, whereas mass flow lets the entire sugar powder flow in as a one bed. And actually there was a secondary unit where they had hammer mills crushing the sugar into fine icing sugar, and that was the primary area of explosion, and then that got carried over to the entire plant. And then we could have also minimized the formation of dust layers. So we could have minimized the amount of hazardous material collecting in the plant by removing the dust deposits. And so because the sugar dust is so fine that they leaked from worn out seals, loose equipments, breaches, and also the bucket elevators that carried the sugars into the hammer mills. And here house maintenance was very crucial, which was often neglected, and the schedules were not followed properly. And then we could have also minimized the volume of process equipment. A general rule of thumb is that the volume of process equipment should not be larger than the volume required by the process, but industries often have silos that have considerably large volumes, and they store it for longer periods of store the product for longer periods of time. They don't remove it, and then so if an explosion happens, then all of that material can act as a fuel for that explosion. Next slide, please. Yes, so we could have also substituted the explosive materials where possible. So we cannot substitute the sugar dust, but then in order to allow the icing sugar to flow, the company added silica. No, the company added starch beads, and starch beads also has this similar problem of combustion. So we could have switched the starch beads and then added silica beads instead. And then we could have also substituted a work procedure. The sugar dust that was getting accumulated on the equipments was being removed by the workers using compressed air, and that created sugar clouds, and then that same dust got accumulated on larger the overhead pipes where normally housekeeping didn't clean. So that over a period of time, the entire factory had large quantities of sugar dust, which finally uh, got ignited due to the initial explosion. And we could have also, as mentioned earlier, we would have changed the hopper design to make a mass flow possible rather than funnel flow. Next. Okay, so here we have done with so the next is
just so did they in this article did they say that this could have been solved by inherent safety, or this is what you kind of thought that there is an opportunity to apply these principles of inherent safety?
no, so we came up with these solutions.
You came up with
They just had a primary report of
looks like
what
when
happened.
I was looking at this, the two which probably seem to be most applicable, one is the minimize, which you talked about, okay, because I think in the first place you need to reduce the formation of dust. That's the most basic thing, and the second thing is that if dust is formed, then it should be less hazardous, which I think the moderation with silica, tends to achieve. It seems that these are the two where probably there's the best chance of applying the principles. I don't know whether you feel the same way. When I was reading this, this is what came to my mind.
Yes, sir. So the next is we're talking about Trevor Klotz, the father of inherent safety. Next. Okay, so Trevor Klotz actually attended Liverpool University and he studied chemistry as his undergraduate major. And then he just joined ICI because it was a very well-known company then. And he joined with an expectation that he would be working in the lab, doing like working with test tubes and doing very fundamental research. But then ICI had a culture of researching in engineering problems rather than chemistry. So he just ended up solving engineering problems in his 7 years. And then indirectly, he became a master in chemical engineering. Next slide. Okay, so after 7 years, he got promoted to plant manager where he ran plants and he did troubleshooting. And then he observed the foreman, and then he realized that even without any up-to-date operating manuals, the foremen had their own philosophy of working around problems. And he also learned something about managing people, and he thought that good natured persistence got him places where other things did not. And those 12 years of experience raised his interest in process safety, and then he began thinking in that direction. Next slide. Okay, so Tanvi Varadkar will be taking on from here.
Yeah. So Kletz's first formal safety assignment came to him in 1955 when he was assigned the role of a part-time safety officer at ICI. And back then, nobody really paid much attention to safety, and they did not realize that it required some kind of a technical input. To them, safety was all about removing mechanical hazards and wearing protective clothing. A lot of times it is thought that HAZOP is actually Kletz's brainchild, but that is not true. There was a culture in ICI where the engineers there practice something known as critical examination of plants. And Kenji, a production manager with ICI, used this technique of critical examination to design a new phenol plant. And this technique helped him discover many potential hazards as well as operating problems well beforehand. Being inspired by what Kenji had worked out, Klotz decided to follow this tradition in ICI, and he was the one who termed that critical examination as hazard and operability study. And he became an enthusiastic advocate of HAZOP. Next. Later on, a very new position was given to Trevor Klotz, which was a technical safety advisor, because he was one of the only people in his peers who showed more interest towards the safety aspects in a chemical plant. And they needed someone who had a very strong technical background, and Trevor fit that designation. His job was basically to advise designers and operating staff on how to avoid accidents. And he realized that this task was very challenging, but that was the thing about Trevor Klotz. He had a very strong technical background, but he also had great people skills. And he realized that convincing people was possible through persistent persuasion, and by showing them the consequences of bad practices and design, and sharing with them the lessons of accidents that had happened previously. Next. Another challenge that Klotz faced as the safety advisor was to ensure that safety lessons were never forgotten. And he emphasized a lot about this in his own autobiography called By Accident, where he said that it is not sufficient to check that rules are being followed, or people will stop following them as soon as attention decreases towards a certain event. We have to convince people that they should be followed, that safety cannot be taken lightly, and it has to become an integral part of the daily workings of a plant. CLETS held weekly briefings with representatives from different departments in ICI and had open discussions with them about safety issues. He also started compiling a series of safety newsletters, which were primarily for plant managers, designers, and maintenance people at ICI. But these newsletters became a huge success. And towards the end of his career, when he retired in 1982, over thousands of people at ICI as well as outside ICI started acknowledging his newsletters and started applying his tenets in their respective industries. Next. This is a link for his newsletters in case anyone is interested. Tanvi Apte will continue now.
So during his tenure as a safety advisor in ICI, he noticed many accidents had taken place, and these accidents could have been easily avoided had inherent safety principles been applied to them. So he consolidated them and wrote a review about them in his article, What You Don't Have Can't Leak. And in his book he also published a book called Process Plants, a handbook for inherently safer design. And in it, he has explained those 4 principles which we mentioned earlier of minimize, moderate, substitute, and simplify. And it's also interesting to note that although inherent safety seems very obvious at this point, it took a long time for engineers to conceive that idea and come up with it. Even after it was conceived, it was not widely accepted for a very long time. So during his 14 years at ICI, the fatality rate of the company fell from around 7 fatalities per 108 working hours to 2.5 in a matter of 14 years. And so some very large-scale accidents which had taken place during that time, such as the Bhopal gas tragedy, could have also been the damage could have been minimized, or it could have been avoided altogether had Trevor CLET's tenets of inherent safety been applied to them. And at this point, the most important contribution of Trevor was that he gave process safety a certain respectability, and also during that time, safety was something that was done after the design process was over, because it was seen as a way of controlling damage. But because of
fatalities per 108 working hours is something missing. 108 seems so low. Is it?
I think it must have been 14 out of 306, and they probably reduced it to 100.
Just have a look at it. Huh? Maybe there is a 1,000 or million or something, you know. Just have a look at it. Okay.
So yes, so that's what I was concluding. That because of him, people started becoming more aware that safety can be applied at the design stage itself instead of doing it at the end of the design procedure. So yes, so that's the end of our presentation.
Okay. Okay. Thank you. And as you said in your last slide, it's really common sense and now used for common practice, right? That's nice. Okay. Thank you so much, everyone.